In the constellation of Ophiuchus lies a modest star that once shook the foundations of cosmology. Astronomers catalogued it as HD 140283, but they gave it another name that would capture the imagination of scientists and the public alike. They called it the Methuselah star, after the biblical figure who was said to have lived longer than any other. The name was fitting. When its properties were first measured, astronomers reached an age of nearly 14.5 billion years. Yet according to the best evidence, the universe itself is only about 13.8 billion years old. Here was a paradox that seemed to whisper of impossibility. Could a star truly be older than the cosmos? The contradiction was startling, but it was never an invitation to abandon the Big Bang or to doubt the framework of physics. Instead, it was a lesson in how precision and uncertainty coexist in science. Every number is bounded by assumptions, models, and measurements. When those limits converge in unexpected ways, nature can appear to defy logic. The Methuselah star was not a refutation of cosmology. It was an extraordinary reminder of how fragile our reconstructions of time can be. To understand why this paradox mattered, we must first step back and ask what it means to know the age of the universe at all. Unlike a star or a planet, the cosmos does not have a surface we can touch, nor layers that can be peeled, like rings of a tree. Its age is inferred through light that has traveled across unimaginable distances, carrying with it the memory of early events. The most important of these signals is the cosmic microwave background, a faint glow that bathes the entire sky. This radiation is the cooled afterglow of the Big Bang, still whispering to us from nearly 14 billion years ago. In the early 1960s, two radio engineers, Arno Penzias and Robert Wilson, stumbled upon a persistent hiss in their antenna. They at first thought it was interference, perhaps from the city nearby, or even from pigeons nesting inside the equipment. But what they had found was the oldest light in existence, a perfect relic from the time when the universe was only a few 100,000 years old. This discovery confirmed predictions made years earlier and opened a new way to measure cosmic time. By mapping the faint variations in this radiation, scientists could reconstruct the composition of the cosmos, the density of matter, and the rate at which space had expanded. Decades later, satellites such as COBE, WMAP, and Planck refined this map with exquisite precision. Each instrument revealed delicate ripples in the microwave background, patterns only a fraction of a degree different from one another, but packed with meaning. These ripples were fingerprints of the early universe, showing how matter clumped and how energy spread. Out of them came one of the most precise measurements in all of science: the age of the universe, 13.7 billion years, with an uncertainty of only about 40 million years. On the scale of cosmic history, that is the difference between a person guessing their age to within a single day. But the microwave background is only one of the tools. Another comes from the expansion itself. In the 1920s, Edwin Hubble looked at galaxies far from the Milky Way and realized that almost all of them were receding. Their light was stretched, shifted toward the red end of the spectrum. The farther away they were, the faster they moved. This became known as Hubble's law, a cornerstone of cosmology. If we know the expansion rate today, we can, in principle, run the film backwards and find the moment when everything was compressed to a single point, the birth of the universe. Yet the story is not that simple. Expansion is not constant. Gravity slows it, while an enigmatic force known as dark energy accelerates it. Matter collapses into galaxies and clusters that change the fabric of space. To account for all these influences, cosmologists rely on general relativity and on nuclear physics. They model how space bends, how matter behaves, and how elements formed in the first minutes after the Big Bang. The chemistry of that brief epoch, when hydrogen fused into helium and traces of lithium, gives another marker. By measuring how much helium and lithium remain in the oldest stars, scientists confirm the consistency of their models. These independent approaches, from expansion to chemistry to radiation, converge on nearly the same number for the age of the universe. The convergence gives confidence, but not certainty. Even within the tight bounds of measurement, a tension lingers. The expansion rate measured from the early universe through the cosmic microwave background yields a value that points to an older cosmos. But when the expansion is measured using nearby galaxies, pulsating stars known as Cepheids, and the bright explosions of supernovae, the numbers suggest a faster expansion, which implies a younger universe. This discrepancy, known as the Hubble tension, is one of the great unsolved puzzles of modern cosmology. Whether it arises from hidden errors or from new physics, it is a reminder that cosmic time is still a work in progress. It was into this landscape of precision and uncertainty that the Methuselah star entered. When its light was measured and compared against stellar models, its age seemed to stretch not only close to the cosmic boundary, but beyond it. To some, this might sound like a contradiction so severe it undermines the Big Bang itself. Yet to astronomers, it was something subtler. It was a paradox that demanded attention. The universe, as far as all other evidence indicated, was about 13.8 billion years old. The star, as far as stellar models suggested, was about 14.5 billion years old. Somewhere, in the overlap of methods and assumptions, lay the answer. This paradox is not a flaw in science, but its strength. It shows that anomalies do not destroy theories, they sharpen them. They point the way toward improvements in instruments, refinements in models, and new insights about the cosmos. The Methuselah star, by seeming to defy the age of the universe, became a guide. To follow its story is to step deeper into the machinery of cosmology, to learn how time itself is measured on the grandest scales. And it is here that our journey begins. The question of cosmic time cannot be answered by a single line of evidence. It emerges instead from a tapestry of methods, each one rooted in different aspects of physics, each one carrying its own uncertainties. The cosmic microwave background is one of the most celebrated because it is both ancient and precise. Yet even this signal requires interpretation through models, and the models depend on assumptions about dark matter, dark energy, and the exact values of fundamental constants. These assumptions cannot be taken for granted. If the density of matter were slightly different, if the strength of gravity or the expansion history were adjusted, the age inferred from the background light would change. The precision comes not from one observation, but from the harmony of many. The harmony extends to the chemistry of the early universe. In the first 3 minutes after the Big Bang, protons and neutrons fused in a brief episode of primordial nucleosynthesis. The fireball cooled too quickly for heavy elements to form, but it left behind a predictable ratio of hydrogen to helium, with a trace of lithium. Billions of years later, astronomers measure these abundances in the oldest gas clouds and in ancient stars. The observed ratios match the theoretical predictions with astonishing closeness. This agreement confirms not only the Big Bang, but also the timeline it implies. It provides another measure of age, consistent with the 13.8 billion year figure. Meanwhile, the large-scale structure of galaxies tells a similar story. Clusters of galaxies, filaments stretching across cosmic voids, and the subtle patterns of gravitational lensing all align with a universe that has been evolving for nearly 14 billion years. The age is embedded everywhere, in the background radiation, in the chemistry of matter, and in the distribution of galaxies. Each piece strengthens the case, but the paradox of Methuselah remains powerful precisely because it arises from a different domain. Stars are local objects. They are close enough to be studied in detail, their brightness and spectra measured with direct instruments. If the universe provides one kind of clock, stars provide another, and when those clocks disagree, we are forced to reconcile them. The method by which stars are aged relies heavily on models of stellar evolution. A star begins its life by fusing hydrogen into helium. The balance between gravity pulling inward and pressure from nuclear burning pushing outward defines its structure. Over billions of years, the star's core changes, slowly depleting its hydrogen and altering its brightness and color. By observing a star's current state and comparing it with theoretical tracks of evolution, astronomers can estimate how long it has been burning. The Methuselah star, faint and metal poor, sits at a point in these diagrams that corresponds to extreme antiquity. Yet there are other methods that provide checks. Some rely on the presence of radioactive elements in the star's atmosphere, uranium and thorium, for example, decay over known timescales. If their abundances can be measured, they offer natural chronometers that can confirm or challenge the ages derived from models. In the case of Methuselah, these measurements reinforce the conclusion that it was among the oldest stars known. Still, every technique carries uncertainties. Distances to stars were once one of the largest sources of error. A slight miscalculation in how far away a star is can change its inferred brightness, and thus its place on the stellar evolution diagram. Before the Gaia mission, parallax measurements were less precise, leaving room for large age variations. Chemical compositions add another layer of uncertainty. The amount of helium in a star, for instance, influences how it evolves, but helium lines are difficult to measure directly. Astronomers must infer them, and those inferences carry assumptions. Nuclear reaction rates inside the star, especially those involving carbon, nitrogen, and oxygen, also introduce uncertainties. If the reaction cross-sections are not known perfectly, the models that trace stellar lifetimes may be skewed. The paradox of Methuselah arose not from a single mistake, but from the combination of all these uncertainties converging in one direction. The error bars stacked in a way that made the star appear older than the cosmos. That apparent contradiction was striking, but it was also a clue. It pointed to where improvements were needed, where new missions and better models could close the gap. Science advances precisely at such boundaries. When the numbers align too neatly, it can mean we are missing hidden complexities. When they diverge, it can mean we are glimpsing something new. The Methuselah star was not simply an oddity, it was an experiment written in the sky, testing the consistency of two independent approaches to time. On one side stood the cosmos as a whole, with its microwave background and expanding galaxies. On the other stood a single star, burning quietly for billions of years. That the two did not match was not a reason for despair. It was a reason to look closer, to sharpen the instruments, and to refine the theories. In this sense, the paradox is less about contradiction than about dialogue. The universe speaks to us through its vast background radiation, while stars speak through their light and chemistry. To find meaning, we must listen to both and reconcile their voices. The Methuselah star forced cosmologists and stellar physicists into conversation, bridging scales from the largest structures in the cosmos to the nuclear furnaces of a single star. As this dialogue unfolded, astronomers began to refine the numbers. Gaia's precise measurements of stellar parallax reduced the uncertainties in distance. Improved nuclear reaction data adjusted the models of stellar evolution. The result was an age closer to 13.5 billion years, consistent with the universe within the margin of error. The paradox softened, but the lesson remained. For a time, a star seemed older than the cosmos, and in confronting that possibility, science advanced. Yet even with this resolution, the question of cosmic time remains open in deeper ways. The Hubble tension lingers, suggesting that our picture of expansion may still be incomplete. The Methuselah star reminds us that the problem of time is not settled, but alive, evolving with every new observation. The paradox is not gone, it has simply transformed from a contradiction into an ongoing exploration. And so, the journey continues. To understand how stars become cosmic clocks and how their messages intertwine with the story of the universe, we must step deeper into the science of stellar ages. Only then can we appreciate how a star once appeared to stand outside of time itself. The paradox of Methuselah illustrates the delicate interplay between observation and theory. A single number that seems out of place can ripple through our understanding, forcing us to reconsider what we thought we knew. To the public, the notion of a star older than the universe may sound like a direct contradiction, a fatal flaw in the edifice of cosmology. But to scientists, it is precisely these anomalies that reveal the health of a field. They demonstrate that our tools are sharp enough to find tensions, and that our curiosity is deep enough to confront them, rather than ignore them. In truth, the Methuselah star never truly defied the age of the universe. Its apparent age was always wrapped in uncertainties, and the overlap of those uncertainties created the illusion of contradiction. But that illusion was powerful. It drew attention to the methods by which we measure time itself. It reminded us that the cosmos is not a textbook with tidy answers, but a dynamic, evolving story in which every detail must be tested and retested. The methods used to date the universe are marvels of precision, but they are not free from assumptions. The cosmic microwave background speaks with authority, but its interpretation requires models of dark matter and dark energy that are not fully understood. Hubble's law is direct, but the exact rate of expansion is still under debate, leading to the ongoing tension between early and late universe measurements. Primordial nucleosynthesis confirms the chemistry of the beginning, but it too depends on nuclear physics that must be tested in laboratories. Each of these methods converges on the figure of 13.8 billion years, yet each remains open to refinement. The methods used to date stars are no less complex. Stellar models must account for mass, composition, opacity, convection, and nuclear reaction rates. Observations must account for distances, brightness, and spectra, all of which are prone to error. Even the most precise parallax measurements leave room for adjustment. The Methuselah star sits at the boundary where these complexities meet. Its faint light, stripped of metals, speaks of a time near the dawn of the Milky Way. Its apparent age once spilled beyond the cosmic horizon, but better data have brought it into alignment. Today it is considered about 13.5 billion years old, consistent with the universe within the error bars. The paradox that made headlines has been resolved, at least for now, and yet the deeper lesson is not the number itself, but the process. Science thrives on paradoxes because they force us to refine our understanding. Without the Methuselah star, the Gaia mission might not have been recognized as urgently necessary, nor would stellar models have been scrutinized with the same intensity. The star became a catalyst for progress. It showed that even the smallest point of light can push the boundaries of knowledge, not by overthrowing theories, but by challenging them to become sharper. The story of this star also reminds us of the fragility of cosmic measurements. To say that the universe is 13.8 billion years old is to express extraordinary confidence in our models, but it is also to acknowledge the limits of precision. 40 million years of uncertainty may seem vanishingly small, but it is still the span of time in which entire species rise and fall on Earth. On cosmic scales, we speak with impressive accuracy, but not with absolute certainty. In the end, the paradox of Methuselah dissolves not into failure, but into humility. It teaches us that numbers are never final, that science is a conversation with reality rather than a proclamation of eternal truth. The star is not older than the universe, but in appearing so, it revealed the fragile and beautiful way in which human beings attempt to measure eternity. It showed that even paradoxes are not obstacles, but stepping stones. From here, the journey moves deeper into the hearts of stars themselves. If the universe can be dated by its radiation and its expansion, stars can be dated by their own nuclear rhythms. They are clocks of fire, ticking not with gears but with fusion, telling the story of time through the balance of gravity and light. To understand how a star could appear older than the cosmos, we must explore how these clocks are built and how they can be read with precision. Only then can we see the paradox of Methuselah in its full meaning, not as a contradiction, but as a beacon pointing toward greater knowledge. If the universe can be measured through its expansion and its radiation, stars offer their own clocks, ticking quietly in the darkness. Unlike galaxies or the cosmic microwave background, a star carries within itself a record of time that is written in fire. From the moment hydrogen ignites in its core, the balance between pressure and gravity dictates a lifespan that can be calculated with surprising precision. By learning to read this stellar rhythm, astronomers can estimate ages that reach back to the dawn of the cosmos. And in the case of the Methuselah star, these methods gave us one of the most puzzling results in all of astronomy. At the heart of stellar age dating lies the theory of stellar evolution. Every star begins as a cloud of gas, collapsing under its own weight, until the heat and pressure at the center ignite nuclear fusion. Hydrogen is transformed into helium, releasing energy that shines as starlight. Over time, the reservoir of hydrogen shrinks, and the star's internal balance shifts. It grows brighter or cooler, or expands into a giant, depending on its mass and composition. Astronomers track these changes using models that describe how stars of different masses evolve. The results are drawn as curves on a diagram of brightness versus temperature. These curves, called isochrones, trace the path of stars at different ages. By comparing an observed star to these curves, its age can be inferred. This method has been tested on star clusters, where hundreds of stars of different masses share the same age. In such clusters, the most massive stars evolve quickly and peel away from the main sequence of the diagram, leaving behind a clear signature of how long the cluster has lived. By matching these patterns to theoretical isochrones, astronomers can date clusters with impressive reliability. When the same models are applied to single stars like Methuselah, the uncertainties are greater, but the principles are the same. Its faint light, cool temperature, and chemical makeup place it on the edge of the diagrams, at an age close to the maximum allowed by the universe itself. Another method for reading stellar clocks comes from the decay of radioactive elements. Some heavy elements, such as uranium and thorium, are forged in rare cosmic events, like supernovae or neutron star mergers. These isotopes decay with half-lives of billions of years. If they are present in the atmosphere of a star, their abundances act like natural chronometers. By comparing the ratio of radioactive isotopes to stable ones, astronomers can estimate how much time has passed since the star formed. This technique, called nucleocosmochronology, is difficult because the spectral lines of these elements are faint and hard to measure, but when successful, it provides an independent check on model-based ages. In the case of Methuselah, the presence of thorium confirmed that it belongs among the oldest stars known, though the exact number remains subject to uncertainty. In recent years, a third technique has added even greater power. This is the study of stellar oscillations, known as asteroseismology. Just as earthquakes send waves through Earth that reveal its inner layers, sound waves ripple inside stars. These waves cause tiny changes in brightness and surface motion, detectable with space telescopes like Kepler. By analyzing the frequencies of oscillation, astronomers can reconstruct the density profile of a star, its core size, and its evolutionary stage. This method has revolutionized stellar astrophysics, allowing ages to be measured with unprecedented accuracy. Though Methuselah has not been a prime target for asteroseismology, similar ancient stars have been studied in this way, refining our understanding of the earliest generations of the Milky Way. All of these methods depend critically on the star's chemical composition. A star, rich in heavy elements, evolves differently from one that is metal-poor. Metals change the opacity of the gas, the way light passes through it, and the rate of nuclear burning. The Methuselah star is strikingly metal-poor, containing only about 1 part in 250 of the iron found in the Sunday. This indicates that it formed very early, before successive generations of supernovae had enriched the interstellar medium. Its chemistry marks it as a relic of the early Milky Way, perhaps even predating the full formation of our galaxy. Metal-poor stars like this are not only old, they are fossils of an age when the cosmos was still new. Yet chemical composition also complicates the models. Small differences in the assumed abundance of helium or oxygen can shift the inferred age by hundreds of millions of years. Nuclear reaction rates add further uncertainty. The fusion of carbon, nitrogen, and oxygen proceeds through complex pathways, each with probabilities that must be measured in laboratories on Earth. Slight changes in those probabilities alter the lifetimes of stars in models, and therefore their predicted ages. Distance is another key variable. To know a star's true brightness, its distance must be measured accurately. Parallax, the apparent shift of a star against the background as Earth orbits the Sun, is the gold standard. But before the Gaia mission, these measurements were imprecise, leaving age estimates vulnerable to error. It was in this web of uncertainties that the Methuselah paradox emerged. Every factor, from distance to chemistry to nuclear physics, tilted the result toward greater age. When combined, the effect was striking. A star apparently older than the universe itself Though later refinements would bring the number down, the paradox remains a powerful lesson in the limits of precision. The methods of stellar age dating are among the most remarkable achievements of modern science. To measure the lifetime of a distant sun-like object is to read time itself, written in light. But these methods also remind us of humility. Stars are not clocks in the everyday sense. Their ticking is slow, shaped by processes that we cannot observe directly. We rely on models, on indirect signatures, and on assumptions that must constantly be tested. The Methuselah star teaches us that even with the best tools, uncertainties remain, and those uncertainties are precisely where discovery waits. The notion of stars as clocks is both intuitive and strange. Intuitive because their lives follow predictable sequences. Strange because the timescales involved are so immense that they escape everyday imagination. To think of a star as an hourglass is to picture grains of hydrogen slowly fusing into helium, each grain releasing light and heat. Billions of years pass as this nuclear sand flows, and when the core is exhausted, the star swells into a red giant, shedding its outer layers and leaving behind a remnant. The pace is steady, governed by the laws of physics, and that steadiness makes stars into natural timekeepers of the cosmos. The technique most widely used by astronomers is called isochrone fitting. The word itself comes from Greek roots, meaning equal time. It describes the theoretical curves that show where stars of a given age should lie on a diagram of brightness versus temperature. These diagrams, known as Hertzsprung-Russell diagrams, are among the most powerful tools in astrophysics. They reveal how stars move through life in a sequence that depends only on mass and composition. By plotting a star on such a diagram and comparing its position to isochrones, astronomers can estimate its age. The challenge lies in the details. Isochrones are sensitive to assumptions about chemical abundances, mixing processes in the star's interior, and the treatment of convection. Different research groups may produce slightly different sets of curves, leading to different inferred ages. Despite these difficulties, isochrone fitting has been used with great success on clusters of stars. In a cluster, every star formed at the same time from the same cloud of gas, but with different masses. The most massive stars evolve quickly and peel off the main sequence of the diagram first. The point at which this turnoff occurs is like a timestamp, indicating the cluster's age. Observations of globular clusters, the dense balls of ancient stars that orbit the Milky Way, show ages of about 12 to 13 billion years. These clusters are nearly as old as the universe itself, and the Methuselah star fits naturally among them as one of the earliest survivors. Nucleocosmochronology adds a different perspective. The idea of using radioactive elements as clocks goes back decades, but it has only become practical with advances in spectroscopy. The half-life of uranium-238, for example, is about 4.5 billion years, while thorium-232 has a half-life of about 14 billion years. By comparing the ratios of these isotopes to stable elements in a star, scientists can estimate how long the radioactive decay has been occurring. In principle, this method is straightforward. In practice, it is challenging because the lines of uranium and thorium in a stellar spectrum are faint and often blended with other features. Even so, measurements have been made in a few extremely old stars, confirming that their ages approach the age of the universe. The Methuselah star's thorium abundance is one of the clues that place it at more than 13 billion years old. Astroseismology, the study of stellar oscillations, adds a third dimension. Stars ring like bells, though the notes are inaudible to human ears. The pressure waves and gravity waves inside a star create surface pulsations that change its brightness by tiny amounts. Satellites, such as Kepler and TESS, have recorded these pulsations across thousands of stars. Each oscillation frequency corresponds to a specific internal structure, just as different notes on a drum reveal its size and shape. By analyzing the oscillation spectrum, astronomers can deduce the size of the core, the rate of hydrogen burning, and the stage of evolution. This allows ages to be measured with extraordinary accuracy, in some cases within a few percent. While the Methuselah star has not yet been studied extensively with this method, other ancient stars have, and the results reinforce the conclusion that some stars are nearly as old as the universe itself. Taken together, these three techniques provide a web of evidence. Each one has limitations, but they complement each other. Isochrone fitting is powerful, but model-dependent. Radioactive dating is direct, but difficult to measure. Asteroseismology is precise, but requires long observations with space telescopes. When all three point toward extreme antiquity, as in the case of the oldest halo stars, astronomers gain confidence in their conclusions. The Methuselah star sits at the intersection of these methods, carrying the combined weight of evidence that it was born in the earliest chapter of cosmic history. Yet the story is not only about technique, it is also about perspective. To think of a star as more than 13 billion years old is to confront timescales that dwarf human history. Civilizations rise and fall in the blink of a cosmic eye. Planets form and erode while the star remains largely unchanged. The Methuselah star has witnessed the assembly of the Milky Way, the birth of countless generations of stars, and the emergence of life on Earth. Its light has traveled to us across the ages, carrying not only photons, but also the message that time itself can be read in the fires of the cosmos. As with all clocks, however, calibration is essential. If the hourglass of hydrogen and helium is to be trusted, we must be sure we understand how quickly the grains fall. That means refining nuclear reaction rates in laboratories, improving models of stellar convection, and measuring distances with ever greater accuracy. Every improvement narrows the uncertainties, and every narrowing sharpens the paradox. The Methuselah star reminds us that clocks do not tick in isolation. They are part of a network of evidence that must be read together if we are to tell the story of the universe with confidence. The search for stellar ages is not only about satisfying curiosity, it is about building a chronology of the cosmos, a history book written in light. Each old star is a page in that book, and the Methuselah star is one of the very first. To read its age is to place a marker close to the beginning of the universe, a boundary that tests whether our models of cosmology and nuclear physics can be trusted. In this sense, the paradox of Methuselah is less about one unusual object and more about the framework of science itself. Consider the role of uncertainty. In everyday life, we often think of numbers as exact. The clock on the wall tells us it is 7:30, not 7:30 plus or minus 2 minutes. But in science, every number comes with a margin of error. When astronomers declare that the universe is 13.77 billion years old, they do so with an uncertainty of about 40 million years. When they state that the Methuselah star is 13.5 billion years old, the uncertainty is about 700 million years. These margins overlap, meaning that, in reality, the paradox is not a contradiction, but a matter of perspective. Yet the dramatic phrasing that a star could be older than the universe captures attention, and in capturing it, forces us to look carefully at the assumptions behind each number. Distance is a prime example. Before the Gaia satellite, parallax measurements were prone to small but significant errors. If a star is slightly closer than assumed, its true brightness is lower, which alters its inferred age. Gaia's precision reduced these errors to a fraction of a percent, and the result was a younger age for Methuselah, bringing it into harmony with the universe. Nuclear physics offers another example. The rates at which carbon, nitrogen, and oxygen participate in fusion affect how long a star of given mass can burn. Measurements of these rates in particle accelerators have gradually improved, refining the models and reducing the ages of the oldest stars by just enough to fit within the cosmic boundary. These refinements do not erase the paradox, they elevate it. They show that science does not collapse when confronted with contradictions, but grows stronger. The tension between the Methuselah star and the age of the universe became a driving force for better instruments, better models, and deeper collaboration between fields. Cosmologists studying the cosmic microwave background and stellar physicists modeling nuclear burning found themselves united by a single star. In reconciling their numbers, they advanced both disciplines. There is also a philosophical lesson in all of this. The idea of time itself is not as simple as the ticking of a clock. Cosmic time is a measure of expansion, tied to the fabric of space. Stellar time is a measure of nuclear burning, tied to the balance of mass and light. To compare them is to compare different languages of nature. That they agree at all is extraordinary. That they sometimes appear to disagree is inevitable. It is in the effort to translate between them that knowledge is gained. The Methuselah star remains a symbol of this effort. Its age has been refined downward, but its significance has only grown. It represents the edge of what is knowable, a place where uncertainties converge and demand resolution. To call it a paradox is not to suggest failure, but to recognize that progress is born from tension. Stars like Methuselah serve as milestones, guiding us toward a more complete understanding of the universe. As we move forward, the focus will shift from methods of measurement to the star itself, to the detailed portrait of HD 140283. By studying its motion, its chemistry, and its place in the Milky Way, we will see how this single point of light became a central character in the story of cosmic time. And in doing so, we will glimpse not only the age of a star, but the path by which science turns puzzles into clarity. The Methuselah star is, in appearance, unremarkable. Through a modest telescope, it looks like any other faint star, no different from the countless points of light that make up the backdrop of the night sky. And yet, hidden in its spectrum, in its motion, and in its chemistry, lies one of the most compelling stories in modern astronomy. Its catalogue name, HD 140283, points to its inclusion in the Henry Draper catalogue, a vast early 20th century survey of stellar spectra. But the star itself was born long before Henry Draper, long before Earth formed, long before the Milky Way had taken its present shape. It is a relic from the time when the first galaxies were assembling, and its survival to this day allows us to hold a fragment of the universe's youth within our telescopes. Located in the constellation of Ophiuchus, the Serpent Bearer, the Methuselah star is about 190 light-years from Earth. That may sound distant, but by cosmic standards, it places the star in our galactic neighborhood. It shines at magnitude 7.2, too faint to be seen with the naked eye, but accessible to even a small backyard telescope. Its proximity has been essential, for it allows astronomers to measure its properties with unusual precision. Distance is the foundation of stellar astrophysics. Without knowing how far away a star is, its true brightness cannot be established, and without brightness, its age cannot be inferred. The Methuselah star's distance was measured through parallax, the tiny annual shift against background stars, caused by Earth's orbit around the Sunday. Early parallax values introduced uncertainties that exaggerated its age. The Gaia satellite, with its unprecedented accuracy, later refined this measurement, reducing the star's apparent age and bringing it into line with the age of the universe. Chemically, the Methuselah star is striking. Its atmosphere contains only a trace of elements heavier than helium. Astronomers refer to these as metals, and in this case, the iron abundance is only about 1/250th that of the Sunday. Such extreme metal poverty marks it as belonging to the second generation of stars, what astronomers call population 2. The first generation, population 3, would have been born from the pure hydrogen and helium of the Big Bang, with no heavy elements at all. Those stars are believed to have been massive and short-lived, leaving behind no survivors today. The Methuselah star, with its low but non-zero metallicity, is likely a descendant of those first stars. It formed from gas that had been ever so slightly enriched by the explosions of the earliest supernovae. Its chemistry tells us it was born when the universe was still young, before multiple cycles of star formation had built up the chemical richness we see in the Milky Way today. The star's motion through space also speaks of its antiquity. It is a halo star, moving in a long, looping orbit that carries it far above and below the plane of the Milky Way. Unlike the thin disk of stars that make up the spiral arms, halo stars are ancient wanderers, relics of the galaxy's formation. The Methuselah star races across the sky at more than 1 kilometer per second relative to the Sunday. Its high velocity and eccentric orbit suggest that it may have originated outside the Milky Way altogether, perhaps captured from a dwarf galaxy that merged with our own in the distant past. In this way, The Methuselah star is not only a chronometer, but also a messenger, carrying information about the Milky Way's earliest mergers and the assembly of our galactic halo. The paradox arises because when astronomers placed all these clues together, the age they inferred stretched beyond the cosmic boundary. Isochrone fitting placed it at about 14.5 billion years old. Radioactive dating with thorium reinforced its extreme antiquity. Even allowing for uncertainties, the central value was older than the 13.8 billion years of the universe. To say a star is older than the cosmos is logically impossible, and yet the numbers demanded to be taken seriously. For years, the Methuselah star stood as a puzzle, its light seeming to outshine the very birth of time. The reaction in the scientific community was not panic, but curiosity. No one believed that the star truly preceded the universe. Instead, the question was how the methods might be misleading us. Was the distance overestimated, making the star appear brighter and therefore older? Was the helium content misjudged, altering the stellar models? Were the nuclear reaction rates inside the star slightly different than assumed? Each of these possibilities was explored in detail, not only for Methuselah, but for other ancient stars as well. The star became a touchstone, a case study in how precision astronomy confronts apparent contradictions. Yet beyond the technical debates, the Methuselah star captured public imagination. Headlines around the world declared that a star had been found older than the universe. To many, it sounded like a paradox straight out of science fiction. Could the Big Bang be wrong? Could our understanding of time itself be flawed? The truth was more subtle, but no less exciting. The paradox did not undermine cosmology. It highlighted its maturity. To even notice such a discrepancy required instruments and models of extraordinary accuracy. The very existence of the paradox proved that science had reached a level of precision where the boundaries of error could be tested against one another. In the Methuselah star, we find not only an astronomical object, but also a symbol of scientific progress. It shows how anomalies become opportunities, how contradictions become the seeds of refinement. The star's age may have been exaggerated by early measurements, but the effort to resolve that exaggeration led to better data, better models, and a deeper understanding of both stars and the universe. Its paradox was not a stumbling block, but a stepping stone. And so the Methuselah star became famous, not because it truly broke the rules, but because it invited us to explore how the rules are known. To see its significance, we must look not only at the star itself, but also at the tools by which its age is measured, and the way those tools intersect with cosmology. The paradox is resolved only when we bring together the story of stellar physics and the story of the universe as a whole. The portrait of the Methuselah star is built from light alone. Each photon that reaches our telescopes has traveled across nearly 200 light-years of space, carrying within it information about the star's temperature, chemical composition, and motion. When this light is passed through a spectrograph, it splits into a rainbow marked by dark lines. Each line corresponds to an element, each element a clue to the star's history. In Methuselah's spectrum, the lines of iron, calcium, and magnesium are faint, testifying to the scarcity of heavy elements. The dominance of hydrogen and helium, along with traces of oxygen and other light elements, confirms its status as an ancient star. Spectroscopy also reveals its velocity. The Doppler effect shifts the star's absorption lines depending on whether it is moving toward or away from us. Combined with proper motion measured by precise imaging, astronomers can reconstruct its orbit around the Milky Way. Methuselah follows a path that is unlike the nearly circular orbits of young stars in the galactic disk. Its orbit is elongated, plunging through the galactic plane and carrying it thousands of light-years above and below. Such orbits are characteristic of halo stars, the oldest population of the galaxy, many of which were likely captured from smaller galaxies long ago. Methuselah's motion suggests it is a relic from the epoch of galactic formation, preserved through more than 13 billion years of cosmic evolution. The determination of its age has been a long journey. In the early 2000s, using data from the Hipparcos satellite, astronomers estimated Methuselah to be about 16 billion years old. Even then, they recognized that uncertainties in distance and composition could shift the result. Later, improved parallax measurements lowered the age to about 14.5 billion years. This was still uncomfortably high, appearing to exceed the cosmic boundary. Only with the arrival of Gaia's precise astrometry did the value settle closer to 13.5 billion years, consistent within uncertainties with the universe itself. Each step in this refinement tells a story of progress in observational astronomy. But the paradox is not simply about one star. It is about the methods we use to measure the passage of time. In Methuselah's case, the brightness and color matched stellar models of extreme antiquity. Its thorium abundance confirmed the impression. The uncertainties aligned in such a way that the number initially overshot the universe's age. Yet this is not unique to Methuselah. Other stars in the halo, and many globular clusters, also approach the cosmic limit. The star's fame comes not from being the only ancient object, but from being the one whose numbers most dramatically pressed against the boundary. The paradox also reveals the importance of error bars, a concept that can seem abstract, but is fundamental to science. When astronomers publish an age of 14.5 billion years with an uncertainty of plus or minus 800 million years, they are not claiming that the star is certainly older than the universe. They are acknowledging that the true age could be as low as 13.7 billion years, or as high as 15.3. Within that range lies the truth. The apparent contradiction vanishes when uncertainties are respected. The paradox is therefore not a flaw in the data, but a lesson in how to interpret it. Still, there is something poetic in the way Methuselah's numbers align. To have a star so old, so metal-poor, and so near to Earth is a stroke of luck. It allows us to study directly an object that formed soon after the universe began. It is like finding a living fossil, a creature unchanged since the earliest era of life on Earth. The Methuselah star has been shining since before the Milky Way was complete, since before the solar system was born, since before our planet had even a hint of its future life. It is a survivor, carrying the memory of an epoch otherwise lost to time. For astronomers, this survival is a gift. Most of the stars born in the early universe were massive and short-lived, burning brightly and dying in supernovae that enriched the cosmos with heavier elements. Very few small, long-lived stars from that epoch remain. Methuselah is one of them. Its mass, slightly lower than that of the Sun, has allowed it to burn slowly and steadily for billions of years. It is a window into the conditions of the early galaxy, and its study informs not only cosmology, but also galactic archaeology, the effort to reconstruct the history of our Milky Way from the properties of its stars. In many ways, Methuselah is less a paradox and more a teacher. Its apparent age greater than the universe forced astronomers to confront the limits of their models. Its refinement to 13.5 billion years demonstrated the power of new missions and new physics. It shows that science advances not by ignoring contradictions, but by embracing them. The star may no longer be thought older than the cosmos, but its story remains one of the most compelling in modern astronomy. The mystery of Methuselah leads us naturally to a deeper question. If one star can carry such tension, what of the broader population of ancient stars? How do globular clusters, stellar streams, and other halo stars compare in age? And how do they together paint a picture of the Milky Way's earliest days? To answer these questions, we must widen our view from one paradoxical star to the relics of the first generations, the fossils that populate our galaxy and whisper of the universe's youth. The legacy of the Methuselah star lies not only in its numbers but in the questions it raised. At first glance, it seemed to stretch beyond the universe itself, daring us to imagine what it would mean for a star to be older than everything around it. The paradox was quickly recognized as an artifact of uncertainties, yet the effect it had on the scientific imagination was profound. It became a catalyst for progress, forcing the community to sharpen every step in the chain of reasoning that leads from starlight to cosmic chronology. One of the most important outcomes was the realization that stellar physics and cosmology cannot be pursued in isolation. The age of the universe is not simply a number from the cosmic microwave background, and the age of a star is not simply a result from isochrone fitting. Both rely on the same underlying physics of matter, radiation, and nuclear reactions. Both are vulnerable to assumptions about constants and abundances. By confronting the Methuselah paradox, astronomers were reminded that progress requires cooperation across disciplines. The boundary between stellar astrophysics and cosmology is porous, and in that porosity lies the strength of science. The Methuselah star also illustrates the nature of scientific storytelling. Data alone do not capture attention. It was the framing of the star as older than the universe that drew headlines and stirred public wonder. The phrasing was technically misleading, but it carried a kernel of truth. The star's age estimate did overlap with or exceed the accepted age of the cosmos. By communicating the paradox, scientists not only engaged the public, but also invited deeper scrutiny from their peers. The result was a vibrant discussion that pushed the field forward. The story shows that anomalies are not merely technical details. They are narrative engines that propel science into new territory. Even now, with Gaia's refined measurements and improved stellar models, the Methuselah star continues to occupy a special place. Its age of about 13.5 billion years makes it one of the oldest known stars in the galaxy. Its low metallicity marks it as a second-generation object, formed from gas that had only barely been enriched by the first supernovae. Its orbit through the halo connects it to the earliest mergers of the Milky Way, and its proximity to Earth makes it a precious target for detailed study. Few stars combine all these qualities. Methuselah is not just ancient, it is accessible, a bridge between the infancy of the cosmos and the precision of modern astronomy. For the scientific community, the paradox is largely resolved. No one now believes that Methuselah is older than the universe. Yet the episode remains a case study in how science operates. Numbers are not sacred. They are tools, refined with each new measurement. Contradictions are not fatal. They are opportunities for discovery. The Methuselah star demonstrates that even a single object, studied carefully, can shape the trajectory of an entire field. It shows how the universe reveals itself through anomalies, and how patience, precision, and humility transform those anomalies into understanding. The journey of Methuselah is not complete, for the star continues to burn. In time, billions of years from now, it will exhaust its hydrogen and swell into a red giant, eventually leaving behind a white dwarf that will cool into darkness. But for now, it shines as a steady reminder of cosmic antiquity. It carries the memory of an age close to the beginning, when galaxies were young and the first heavy elements were forged. To study it is to touch the past, to see in the present sky a fragment of a time that shaped everything we know. The paradox of Methuselah was never about proving the universe wrong. It was about testing the boundaries of what we can know. And in doing so, it taught us that science is not the search for certainty, but the pursuit of ever sharper approximations. The star is not older than the universe, but in seeming to be so, it revealed the beauty of inquiry, the power of anomalies, and the endless potential for discovery. As we leave the story of Methuselah itself, we turn to the broader question of measurement. If a single star can appear to defy cosmology, what does this say about the tools we use to measure time? The answer lies in examining not just the star, but the methods. To truly resolve the paradox, we must explore how measurement errors, assumptions, and refinements shape the numbers we trust. The next step, therefore, is to examine the uncertainties themselves, to see how the act of measuring both creates and dissolves paradoxes. Every paradox in science is built not only from nature, but from the way we measure it. The Methuselah star seemed to be older than the universe not because it truly was, but because the process of translating light into age is delicate and vulnerable to small shifts. The story of this paradox is therefore not just about stars and cosmology. It is about measurement itself, about how precision can both illuminate and deceive. To see why Methuselah appeared so ancient, we must look closely at the methods that turned photons into numbers and ask where the uncertainties entered. The first and most fundamental measurement is distance. Without knowing how far away a star lies, we cannot know its true brightness. A star might appear faint because it is old and weak, or simply because it is far away. The difference is critical. For brightness, is one of the main inputs to stellar age models. For more than a century, astronomers have used parallax to determine distance. As Earth orbits the Sun, nearby stars shift slightly against the background of more distant stars. The angle of this shift, though tiny, can be measured and converted into distance using simple geometry. For bright, nearby stars, parallax works beautifully. But for stars like Methuselah, almost 200 light-years away, the shift is so small that even advanced instruments struggle. Early parallax data, including those from the Hipparcos satellite, carried uncertainties large enough to skew the inferred brightness of Methuselah. When brightness is off, the star's placement on the Hertzsprung-Russell diagram shifts, and with it, the inferred age. It was only when Gaia delivered measurements with unprecedented accuracy that the distance uncertainty was reduced to the point where the paradox could soften. Another crucial measurement is chemical composition, the ratio of hydrogen to helium, and the trace presence of heavier elements shapes a star's life. Helium in particular plays a central role, for it alters the density and pressure of the core, changing how quickly hydrogen burns. But helium leaves few direct spectral lines, making it difficult to measure. Astronomers often infer helium abundance indirectly, from the star's metallicity, or from theoretical assumptions about galactic chemical evolution. A small error in helium estimation can shift a star's predicted lifetime by hundreds of millions of years. Methuselah's extreme metal poverty made these inferences even more uncertain, adding to the margin of error in its age. Opacity, the way light interacts with matter inside a star, is another factor. The absorption of photons by ions determines how heat moves from the core to the surface. If opacity values are miscalculated, the star's evolution is modeled incorrectly. Opacity depends on atomic data measured in laboratories, but reproducing the conditions of stellar interiors on Earth is nearly impossible. As a result, opacity carries hidden uncertainties that propagate into stellar models. For Methuselah, these uncertainties meant that its evolutionary path on the diagram might have been slightly misdrawn, exaggerating its apparent age. Nuclear reaction rates are among the most subtle but influential measurements. The fusion of hydrogen into helium proceeds through multiple pathways. In stars like Methuselah, which are poor in metals, the dominant path is the proton-proton chain. But even here, side reactions involving carbon, nitrogen, and oxygen can play a role. The probabilities of these reactions, known as cross-sections, are measured in particle accelerators at energies far lower than those inside stars. Physicists must extrapolate from laboratory data to stellar conditions, and those extrapolations carry uncertainties. A small error in a reaction rate can shift the lifetime of a star by a significant fraction, enough to turn a 13 billion year age into 14 billion. Even the instruments themselves introduce uncertainties. Telescopes must be calibrated, detectors corrected for noise, spectra disentangled from the effects of Earth's atmosphere. A slight miscalibration of wavelength can change the inferred abundance of an element. A small systematic error in brightness can ripple into large changes in inferred distance. Each of these uncertainties is accounted for statistically, but when they all tilt in the same direction, they can conspire to produce a paradox. Methuselah's apparent age beyond the universe was not the result of one catastrophic mistake, but of many small uncertainties aligning to push the number upward. The resolution came with Gaia. Launched by the European Space Agency, Gaia is designed to map more than 1 billion stars with unprecedented accuracy. Its measurements of parallax are precise to microarcseconds, enough to determine distances to stars thousands of light-years away with less than 1% error. For Methuselah, Gaia's refined distance placed it slightly closer than previously thought. That meant it was slightly fainter in reality than earlier data suggested, and therefore younger in the models. This single adjustment was enough to bring the star's age down from 14.5 billion years to about 13.5, resolving the paradox within uncertainties. Measurement matters not only because it provides answers, but because it defines the questions. The Methuselah paradox was born from the limits of precision. It forced astronomers to consider how assumptions about helium, opacities, and nuclear physics shape their models. It demonstrated that every number is provisional, awaiting better instruments and sharper theories. And it showed that progress in science is often driven less by new ideas than by better measurements. Yet the paradox also reminds us that uncertainties are not failures, they are features. To say that Methuselah is 13.5 billion years old, plus or minus 700 million years, is to acknowledge the limits of our tools, but those limits are what make the science honest. Without uncertainties, there would be no room for refinement, no space for progress. Methuselah's paradox dissolved not because we abandoned cosmology, but because we embraced the uncertainties and reduced them. The story is far from over. Even as Methuselah's age was brought into line with the universe, another tension emerged elsewhere. The expansion rate of the universe, measured in different ways, refuses to agree. Just as Methuselah once seemed to outpace the cosmos itself now seems to carry conflicting clocks. The Hubble tension is the next paradox, one that links the Methuselah star to the deepest questions in cosmology. The refinement of Methuselah's age shows how measurement is as much an art as a science. Numbers do not simply emerge from instruments like water from a spring. They must be extracted, corrected, and interpreted through layers of assumptions. In astronomy, this process is especially delicate because the objects we study are far beyond our reach. We cannot bring a star into a laboratory, weigh it, or cut it open. We must infer its properties from the faint trickle of light that arrives across unimaginable distances. Every stage in this chain, from telescope mirror to theoretical model, is a place where uncertainty can enter. One of the clearest examples of this is parallax. The principle is simple. As Earth moves around the Sun, nearby stars shift slightly against the distant background, but the angles involved are tiny, measured in arc-seconds, a unit so small that it is difficult to imagine. 1 arc-second is the width of a human hair, seen from a distance of 30 meters. For a star nearly 200 light-years away, the parallax is less than 10 milliarc-seconds. Measuring such a shift requires instruments of extraordinary stability. Even the slightest jitter in a satellite's pointing, or the smallest distortion in its optics, can alter the result. Before Gaia, these effects limited accuracy, and Methuselah's distance was uncertain enough to exaggerate its age. Gaia's design overcame many of these limitations, but the lesson remains. Precision is fragile. Chemical abundances provide another example. Astronomers measure the depths of spectral lines to infer how much of an element is present, but these lines are influenced not only by abundance, but also by temperature, pressure, and turbulence in the star's atmosphere. Sophisticated models of stellar atmospheres must be applied to disentangle these effects. For stars as metal-poor as Methuselah, the lines are so faint that they push the limits of detection. Small differences in the assumed model atmosphere can lead to large differences in inferred abundances. And since abundances feed directly into stellar evolution models, the age that emerges depends critically on these details. Laboratory measurements of atomic and nuclear data form yet another layer. To model a star accurately, one must know how atoms absorb light and how nuclei fuse. Opacity tables are built from vast compilations of atomic transitions, each measured or calculated with some degree of uncertainty. Nuclear reaction rates are determined by experiments at accelerators, but the energies inside stars are far lower than can be easily reproduced on Earth. Physicists must extrapolate, and those extrapolations carry errors. These errors propagate upward, shaping the predicted lifetimes of stars. For Methuselah, the uncertainties in key reactions of the proton-proton chain and the carbon-nitrogen-oxygen cycle may have added hundreds of millions of years to its inferred age. All of these uncertainties are carefully tracked. Astronomers publish error bars alongside their age estimates, acknowledging that the number is not absolute, but the public often overlooks these margins, focusing instead on the central value. A headline that proclaims a star older than the universe is more dramatic than one that says a star is nearly as old as the universe within uncertainties. Yet it is precisely the uncertainties that carry the meaning. They tell us where the limits of knowledge lie, and they point to where new discoveries will be made. The Gaia satellite did more than refine distances. It also mapped motions, allowing astronomers to place stars like Methuselah in their galactic context. By tracing its orbit, scientists could confirm that it belongs to the halo, a population of ancient stars that orbit far from the disk. This context strengthens the case for its antiquity, for halo stars are consistently among the oldest in the galaxy. Gaia's contribution was therefore not only a numerical correction but a narrative one, placing Methuselah within the broader story of galactic evolution. The resolution of the paradox illustrates how science works at its best. A problem arises, not because of failure, but because of precision. The problem captures attention, prompting new observations and better models. Over time, the paradox dissolves, replaced by a deeper understanding. Methuselah's age of 13.5 billion years now fits comfortably within the universe's age of 13.8 billion years, both numbers carrying their own uncertainties. The contradiction is gone, but the lesson remains. Measurement is not static. It is a living process that evolves with technology and theory. Yet the story also prepares us for new paradoxes. The Hubble tension, the disagreement over the rate of cosmic expansion, is in many ways the cosmological cousin of the Methuselah paradox. Just as a single star once seemed older than the cosmos, the universe now seems to expand at two incompatible speeds, depending on how the measurement is made. The lesson of Methuselah is that such paradoxes are not signs of collapse, but opportunities for growth. The universe is not lying to us. It is challenging us to measure more carefully, to think more deeply, and to connect our theories across scales. Measurement matters because it is the bridge between observation and theory. Without it, science would be speculation. With it, science becomes a dialogue with nature, a dialogue that is always imperfect, but always improving. The Methuselah star spoke to us through light, and our measurements nearly convinced us it was older than time. By listening carefully, by refining our tools, we learnt not only the truth of its age, but also the fragility of knowledge itself. And in that fragility lies the strength of science, for it is only by acknowledging uncertainty that we can move toward truth. The paradox of Methuselah has largely faded, but its legacy continues to shape astronomy. It showed that when measurements appear to contradict one another, the solution is rarely to discard the framework of science. Instead, the path forward is to examine the details, to refine the numbers, and to uncover where uncertainties have conspired to create the illusion of contradiction. In this sense, the Methuselah star was never a threat to cosmology, but a gift, for it drew attention to the places where precision was most fragile. Every great advance in astronomy has been tied to improvements in measurement. The discovery of exoplanets became possible only when spectrographs could measure stellar wobbles of a few meters per second. The detection of gravitational waves required laser interferometers that could sense changes smaller than the width of a proton. The refinement of Methuselah's age required Gaia to measure stellar positions to microarc-second accuracy, equivalent to detecting the motion of a coin on the moon. Each step shows that measurement is not a background detail of science, it is its beating heart. The case of Methuselah also emphasizes the importance of collaboration. No single field could resolve the paradox alone. Astronomers needed astrophysicists to improve stellar models, nuclear physicists to refine reaction rates, atomic physicists to expand opacity tables, and engineers to design satellites capable of extreme precision. The resolution of the paradox was a triumph, not of one discipline, but of many, woven together in pursuit of a single star's truth. It is a reminder that science is collective, that knowledge is built by networks of effort spread across the globe. And yet, despite this triumph, tension remains elsewhere. The universe is still testing us with puzzles that defy easy resolution. The Hubble tension is perhaps the most dramatic. Measurements of the expansion rate using the cosmic microwave background yield a value of about 67 kilometers per second per megaparsec, while measurements using Cepheid variables and supernovae yield about 73. The difference may not seem large, but it is statistically significant. If the higher value is correct, the universe would be younger, perhaps closer to 12.5 billion years. That would reopen the possibility of stars appearing too old. If the lower value is correct, then the paradox disappears, but new physics may be required to explain the difference. In either case, the lesson of Methuselah prepares us. Paradoxes are not dead ends, they are beginnings. The refinement of the star's age also reflects a deeper truth about knowledge. We often long for certainty, for a final answer that settles a question once and for all. But science does not work that way. Numbers shift, theories evolve, and instruments improve. What matters is not the permanence of the answers, but the continuity of the process. The Methuselah star was once thought to be 14.5 billion years old. Now it is believed to be 13.5. Future refinements may adjust that number again. The universe does not change, but our understanding of it does, and that is the essence of progress. In a way, the Methuselah paradox was a mirror, showing us how fragile and how powerful our methods are. It reminded us that cosmic truths are not revealed in a single stroke, but in the careful accumulation of evidence. It showed that when faced with a contradiction, science does not collapse, but rises to the challenge. And it prepared us for the next paradox, the next tension that will drive us deeper into the mysteries of the cosmos. The paradox of a star older than the universe has been resolved, but the paradox of conflicting expansion rates remains. Just as Methuselah once seemed to defy time, the universe itself now seems to defy its own pace of growth. To understand this new tension, we must follow the thread of measurement from the scale of stars to the scale of galaxies, from the light of ancient relics to the explosions of distant supernovae. Only by doing so can we see how the universe is testing our understanding, and how, in resolving these tests, we move closer to the truth of cosmic time. The universe carries within it a rhythm, the steady stretching of space, that began with the Big Bang and continues today. Astronomers call this rhythm the expansion of the universe, and the number that describes its pace is known as the Hubble constant. It is a value with simple units, kilometers per second per megaparsec, meaning that for every additional megaparsec of distance, a galaxy appears to move away faster by that many kilometers per second. On paper, the concept is straightforward. In practice, measuring it has become one of the great controversies of modern cosmology. The Hubble constant lies at the heart of our understanding of cosmic time. If the universe expands faster, then it must be younger, because it would have reached its current size in less time. If it expands more slowly, then it must be older. By measuring this constant with precision, we not only learn the current rate of expansion, but also infer the age of the cosmos. This is why the Methuselah paradox, the appearance of a star older than the universe, is so closely tied to the debate over the Hubble constant. If the expansion rate is higher than thought, then the universe is younger, and ancient stars push more strongly against its boundary. If the expansion rate is lower, then the universe is older, and the paradox fades. The first attempts to measure the Hubble constant date back to the 1920s, when Edwin Hubble discovered the relationship between distance and recession speed. His early values were wildly inaccurate, more than 10 times larger than today's. That error implied a universe only a couple of billion years old, far younger than Earth itself. At the time, this was a profound problem. How could the universe be younger than the rocks beneath our feet? Over the decades, better instruments and methods refined the value downward, resolving the contradiction. The lesson was clear. Measurement is everything. In the modern era, the debate has sharpened into two competing camps. On one side are the measurements derived from the early universe, particularly the cosmic microwave background. The Planck satellite, which mapped this radiation with exquisite precision, produced a value of about 67 kilometers per second per megaparsec. This number, combined with models of cosmic composition, implies an age of 13.77 billion years. On the other side are the measurements derived from the local universe, using Cepheid variable stars and supernovae as distance markers. These yield a higher value, around 73 kilometers per second per megaparsec, which would imply an age closer to 12.5 to 13 billion years. The difference may appear small, but it is statistically significant, and no simple error seems to explain it. The disagreement has become known as the Hubble tension, and it is now one of the central puzzles of cosmology. It is not just a matter of numbers, but of methods. The cosmic microwave background tells us what the universe was like 380,000 years after the Big Bang. Cepheids and supernovae tell us what the universe is doing right now. If both methods are correct, then the expansion rate has changed in a way not accounted for by our current models. That would imply new physics, perhaps an evolving form of dark energy, or subtle interactions in the early universe that altered the trajectory of expansion. The stakes are high. If the higher value is confirmed, the universe may be 1 billion years younger than we thought, reopening tensions with the oldest stars and clusters. If the lower value is confirmed, then the paradox of Methuselah fades, but we must still explain why nearby galaxies seem to recede faster than predicted. Either way, the answer will shape our picture of cosmic history. The debate is far from settled. Teams around the world are refining their methods, cross-checking assumptions, and building new instruments. The SH0ES project, led by Adam Rees, has pushed the local measurements to unprecedented precision, consistently finding the higher value. Other groups using gravitational lensing, baryon acoustic oscillations, and red giant stars are probing the issue from different angles. Each method carries its own uncertainties, but together they paint a picture of a field alive with tension, searching for resolution. For astronomers, this is both frustrating and exhilarating. Frustrating because the disagreement refuses to vanish, even as precision improves. Exhilarating because history shows that such tensions often precede breakthroughs. When Hubble's original constant gave an impossibly young universe, the paradox led to discoveries about measurement and distance. When Methuselah seemed older than the cosmos, the paradox led to Gaia and better stellar models. The current Hubble tension may be the next such paradox, a sign that our picture of the universe is on the verge of transformation. The debate over the Hubble constant is more than a technical dispute. It is a story about how we measure time itself, about how light from distant galaxies and relic radiation from the dawn of creation combine to tell us the age of everything. And just as the Methuselah star forced us to reconcile stellar ages with cosmic chronology, the Hubble constant forces us to reconcile the universe's past with its present. The numbers will eventually converge, either through improved precision or through new physics. Until then, the tension remains, a riddle at the heart of cosmology. The conflict between the two values of the Hubble constant is striking because both sides are built on solid foundations. The cosmic microwave background is among the most pristine signals in all of astronomy. It is ancient, untouched by dust or galaxies, a direct remnant of the early universe. The Planck satellite measured its fluctuations with such precision that the resulting maps are often described as the most detailed baby picture of the cosmos ever taken. From those fluctuations, cosmologists infer the density of matter, the influence of dark energy, and the overall geometry of space. With those ingredients in hand, the Hubble constant emerges naturally from the equations of general relativity. The result is self-consistent, beautifully matched to the rest of the model, and supported by independent measurements of primordial element abundances and large-scale structure. It is difficult to doubt the reliability of this approach, and yet the Cepheid and supernova measurements are equally compelling. Cepheid variables are pulsating stars whose brightness varies in a way that is directly tied to their intrinsic luminosity. By observing the period of their pulsations, astronomers can calculate how bright they truly are, compare that to how bright they appear, and thus determine their distance. When Cepheids are found in galaxies that later host supernovae, the two methods link together, allowing distances to be measured far into the universe. By comparing those distances with the recession speeds of galaxies, the current expansion rate is derived. The SH0ES project has refined this ladder of measurements to extraordinary accuracy, using the Hubble Space Telescope and now the James Webb Space Telescope, to minimize sources of error. Time and again, the value emerges around 73 kilometers per second per megaparsec. Neither side can be dismissed as mistaken. The cosmic microwave background speaks of the universe as it was in its infancy, the Cepheids and supernovae of the universe as it is today. If the numbers disagree, it may be because the universe is telling us that something changed in the intervening billions of years. Perhaps dark energy, the mysterious force accelerating cosmic expansion, is not constant after all. Perhaps new kinds of particles interacted in the early universe in ways we have not yet imagined. Or perhaps space itself behaves differently on large scales than our theories predict. The disagreement has sparked a flurry of alternative approaches. Gravitational lensing, where the mass of a galaxy bends the light of a more distant object, offers another way to measure cosmic distances. By analyzing the time delays in the multiple images of lensed quasars, astronomers can infer the expansion rate. These methods have tended to support the higher value, lending weight to the Cepheid and supernova side of the debate. Other methods, such as baryon acoustic oscillations, rely on the imprints of sound waves in the distribution of galaxies. These align more closely with the lower value from the cosmic microwave background. Each method adds complexity rather than resolution, deepening the sense of paradox. The consequences reach far beyond a single number. If the higher value is correct, the universe is younger than we thought, perhaps only 12.5 to 13 billion years old. That would bring it into closer tension with the oldest stars and clusters, including Methuselah. If the lower value is correct, the universe remains 13.8 billion years old, but we are left to explain why nearby galaxies expand faster than expected. Either way, the result points to something missing in our understanding, whether in the early universe, the late universe, or both. This is why the Hubble tension is often described as the most pressing problem in cosmology today. It is not simply a debate over decimal places, but a window into the fundamental workings of the cosmos. The answer may reshape our understanding of dark energy, of gravity, or even of the basic assumptions that underlie the Big Bang model. The stakes are immense, for hidden in this disagreement may be the key to the next great revolution in physics. For the moment, the paradox remains unresolved. Astronomers continue to gather data, refine methods, and test assumptions. The James Webb Space Telescope is extending the reach of Cepheid measurements, while future missions like Euclid and the Nancy Grace Roman Space Telescope will map galaxies with unprecedented precision. On the cosmic microwave background side, new ground-based observatories are planned to measure polarization and other fine details that may sharpen the models even further. The debate is alive, and with each new observation, the tension either tightens or begins to give way. The story of the Hubble constant echoes the story of Methuselah. Both reveal the fragility of cosmic measurements, and both show that paradox is the engine of progress. A star that seemed older than the universe forced us to refine stellar ages and distances. A constant that refuses to agree forces us to refine our understanding of cosmic expansion. In both cases, the universe is not contradicting itself. It is inviting us to listen more carefully, to measure more precisely, and to expand the scope of our theories. The persistence of the Hubble tension has changed the mood of cosmology. At first, it was thought to be a temporary problem, a discrepancy that would vanish once measurements improved. But as the precision sharpened, the disagreement did not dissolve, it deepened. Instead of fading into the background, the tension became more robust, surviving repeated attempts at resolution. It is now taken seriously as a possible sign of new physics, just as the paradox of Methuselah was once taken seriously as a sign of the limits of stellar modeling. What might new physics look like? Some researchers suggest that dark energy, the mysterious component driving cosmic acceleration, may not be constant after all. The standard model of cosmology assumes it behaves like a cosmological constant, unchanging over time. But if dark energy evolves, growing stronger or weaker across billions of years, it could alter the pace of expansion in ways that reconcile the two values. Others propose that an unknown form of radiation or matter existed in the early universe, subtly shifting the way the cosmic microwave background maps to today's expansion. Still others explore modifications to general relativity, asking whether gravity itself behaves differently on the largest scales. Each possibility is bold, but history shows that paradoxes sometimes require bold answers. There is also the possibility that the answer lies not in new physics, but in hidden systematics. Cepheid variables may be influenced by environmental factors we do not fully understand. Supernova brightness may depend on subtle details of progenitor stars. The cosmic microwave background analysis may carry assumptions about neutrinos, baryons, or other components that need revision. Science thrives by testing every assumption, and the Hubble tension has become a laboratory for such testing. The implications for cosmic age are direct. If the higher value of about 73 kilometers per second per megaparsec is correct, the universe is about 1 billion years younger than the standard figure of 13.8 billion years. That would place it near 12.8 billion years, and once again the oldest stars, including Methuselah, would press against its boundaries. If the lower value of 67 is correct, the universe retains its age of 13.77 billion years, and the Methuselah paradox fades into history. In this way, the Hubble constant debate is not separate from the story of Methuselah, but a continuation of it, a cosmic echo of the same theme. How do we measure time on the grandest scale? The story is unfinished, and that is what makes it exciting. Just as the Methuselah star spurred missions like Gaia and refinements in stellar physics, the Hubble tension is driving the design of new telescopes and experiments. The James Webb Space Telescope, with its ability to observe Cepheids and supernovae in unprecedented detail, will test the local measurements. The Nancy Grace Roman Space Telescope will map supernovae across cosmic history. Ground-based observatories will measure galaxy clustering and baryon acoustic oscillations with new precision. Each step brings us closer to an answer, though whether that answer will be a resolution or a revelation remains to be seen. For the public, the Hubble tension may seem like an obscure quarrel over decimal places, but for scientists, it is a drama unfolding at the heart of cosmology. The universe has handed us a riddle, and in trying to solve it, we may uncover truths as profound as the discovery of dark energy itself. The debate is not a weakness, it is a strength. It shows that science is alive, that it does not settle into complacency, but constantly tests itself against nature. The Methuselah paradox and the Hubble tension together teach a single lesson. Time is not easy to measure. Whether in the burning of a star or the stretching of space, the numbers are always provisional, always open to refinement. Paradoxes are not signs of failure, but milestones on the path of discovery. To confront them is to do science in its truest sense, to embrace uncertainty and push it toward clarity. As the debate continues, we are reminded that the universe is not obligated to make sense to us. It offers clues, sometimes harmonious, sometimes contradictory, and it is up to us to weave them into a coherent story. The Hubble constant is one of those clues, a number that seems simple, yet carries the weight of cosmic history. To resolve its value is to resolve not just a debate, but the age of the universe itself, and in doing so, we move one step closer to understanding how time flows on the largest possible scale. The Methuselah star is not alone in its antiquity. Scattered across the halo of the Milky Way are other relics of the early universe, stars so old and metal-poor that they serve as fossils of cosmic history. These ancient survivors belong to what astronomers call Population 2, the second generation of stars. Their chemistry carries the imprint of the very first stellar explosions, and their ages press close to the dawn of the cosmos. Together, they form a record of the time when galaxies were first assembling and when the elements of life were just beginning to appear. To understand these relics, we must step back to the earliest times. The Big Bang produced only the lightest elements: hydrogen, helium, and trace amounts of lithium. The universe then entered a long era of darkness, with no stars to shine and no heavy elements to enrich the gas. In this dark age, Gravity slowly pulled matter together into the first dense clumps. When enough mass accumulated, the first stars ignited. These were the population 3 stars, the true pioneers of starlight. Population 3 stars remain a theoretical concept, for none have yet been observed. Models suggest they were massive, perhaps dozens or even hundreds of times the mass of the Sunday. Such giants burned furiously and lived briefly, exhausting their fuel in only a few million years. When they died, they exploded as supernovae, scattering heavy elements into the surrounding gas. These explosions seeded the cosmos with the first carbon, oxygen, and iron, making it possible for the next generation of stars to form with trace amounts of metals. Among these descendants was Methuselah, and others like it, which carry in their atmospheres the fingerprints of those first explosions. The search for population 3 stars has become one of the great quests of modern astronomy. Because they were so massive and short-lived, they are not expected to survive to the present day. Instead, astronomers look for their chemical legacy in the stars that followed. A population 2 star with an exceptionally low metal content is a likely candidate to have formed directly from gas, enriched by only 1 or 2 population 3 supernovae. The specific ratios of elements in such a star act as a chemical fingerprint, revealing the nature of its ancestral explosions. In this way, the relic stars we observe today are windows into a time otherwise inaccessible. Globular clusters are another kind of relic. These dense swarms of hundreds of thousands of stars orbit the Milky Way in its halo, and their ages are among the oldest measured. Many globular clusters date back more than 12 billion years, nearly to the beginning of star formation itself. Their stars are consistently metal-poor, their orbits carry them far from the galactic disk, and their histories trace the assembly of the Milky Way. In studying globular clusters, astronomers learn not only about stellar ages, but also about how galaxies merge and grow. The clusters are fossils not just of stars, but of entire galactic fragments captured long ago. The relics of the first generations are fragile. Many have been torn apart by the tides of the Milky Way, their stars scattered into long streams that arc across the sky. These stellar streams, visible today as faint ribbons of stars, are the remnants of ancient clusters or dwarf galaxies absorbed by the Milky Way. They carry with them some of the oldest stars in existence, survivors of an era when the universe was still young. By mapping their motions and chemistry, astronomers reconstruct the early history of our galaxy. Each star is a messenger from the dawn of time, carrying clues about the conditions under which it was born. The study of relic stars also connects directly to the question of cosmic time. When we date a star like Methuselah or a globular cluster, we are not only learning how old it is, we are testing the timeline of the universe. If the oldest stars are 12 or 13 billion years old, they fit comfortably within the age of the cosmos. If any were older, the paradox would return. The fact that all known relics fall within the cosmic boundary is a triumph of consistency, even if some, like Methuselah, come close enough to test our confidence. For astronomers, the hunt for the most metal-poor stars is a way of pushing back against the limits of observation. Surveys comb the sky for stars with iron abundances as low as 1 part in 100,000 compared to the Sunday. Such stars are thought to have formed directly from gas, enriched by a single population 3 supernova. Their discovery allows scientists to piece together the nature of the first stars, even without observing them directly. In this way, relics of the first generations act as cosmic archaeologists, preserving in their chemistry the memory of a vanished epoch. The Methuselah star may be the most famous, but it is part of a broader family. Together, these relics anchor the timeline of cosmic history. They show us that stars have been burning since nearly the beginning, that galaxies were already assembling when the universe was only a few 100 million years old, and that the elements of planets and life were forged in the fires of those early explosions. To study them is to look back in time, to glimpse the universe as it was when it was still finding its shape. The search for the earliest relic stars is a pursuit of extremes. Astronomers sift through millions of stars to find just a handful with the lowest metal content. These rare objects are known as extremely metal-poor stars, and they are treasured as fossils of the early cosmos. Their atmospheres preserve the chemistry of the gas from which they formed, largely unaltered by the passage of time. Unlike massive stars, which churn their interiors and enrich their surfaces with newly forged elements, these small survivors remain chemically pristine. Observing them is like opening a time capsule sealed for more than 13 billion years. Some of the most remarkable discoveries have been stars with iron abundances less than 100,000th that of the Sunday. Their spectra reveal only traces of heavy elements, often with peculiar patterns. One star might show an excess of carbon, another a deficiency of magnesium, another an unusual ratio of calcium to iron. These patterns are not random. They are the fingerprints of the supernovae that enriched the gas from which the stars were born. By matching the observed abundances to models of stellar explosions, astronomers can reconstruct the characteristics of the long-vanished population 3 stars. In this way, the chemical memory of the first generation survives in the atmospheres of the second. The relic stars also serve as milestones in the assembly of the Milky Way. The halo, with its eccentric orbits and metal-poor populations, is thought to be built from the remnants of smaller galaxies that merged with ours. Each relic star may have originated in a different fragment, a dwarf galaxy now long dissolved. By measuring the motions of these stars with Gaia, astronomers can trace their origins, grouping them into streams and associations that reveal the bones of ancient mergers. The chemical signatures add another dimension, showing which fragments were enriched by which kinds of supernovae. The combined picture is one of a galaxy built from many parts, stitched together over billions of years. Globular clusters stand as grander relics, monuments to the earliest star formation. Each cluster contains hundreds of thousands of stars, bound together in a dense ball. Their ages, measured through isochrone fitting, consistently reach more than 12 billion years. Some clusters may be nearly as old as the universe itself. They are crowded environments where stars interact gravitationally, exchange mass, and evolve in complex ways. Yet their overall antiquity is unmistakable. The Milky Way contains about 150 such clusters, each a fossil galaxy core that has survived from the early epoch of galactic formation. Their stars shine with the light of the first great wave of stellar birth. The mystery of population 3 stars remains. If the first generation was truly massive and short-lived, none should survive to the present. And yet, astronomers still hope to find one. The hope lies in the possibility that some population 3 stars were less massive, perhaps only a fraction of the Sun's mass, and therefore capable of surviving to this day. If such a star exists, it would be the ultimate relic, a direct survivor of the primordial universe. Despite extensive searches, none has been found. But the discovery of ever more metal-poor stars keeps the hope alive. Each new record holder brings us closer to the threshold, and the search continues with unrelenting intensity. These relics are important not only for understanding the early universe, but also for testing the models of cosmic evolution. The abundances of elements in the oldest stars constrain theories of nucleosynthesis, the processes by which the first heavy elements were made. They also constrain models of galaxy formation, showing how quickly enrichment occurred and how efficiently the first stars seeded their surroundings. Without relic stars, we would have only theory to guide us. With them, we have evidence, faint but enduring, written in starlight. The Methuselah star is one of the brightest and best studied of these relics, but it is far from unique. Its paradoxical age drew attention, but its true significance lies in its membership among this family of ancient survivors. Together, these stars form a chorus, each voice carrying the story of a different corner of the early cosmos. By listening to them, we reconstruct a history that stretches back nearly to the beginning, filling in the pages between the Big Bang and the emergence of the Milky Way. In seeking the relics of the first generations, astronomers are not only hunting for data, they are confronting the profound question of origins. How did the first stars light up the universe? How did they forge the elements that would one day build planets, oceans, and life? And how do we, on a small world orbiting an ordinary star, trace our lineage back to those fiery ancestors? The relic stars remind us that the answers are already written in the sky, waiting only for us to learn how to read them. The importance of relic stars goes beyond their role as fossils of the early cosmos. They are also keys to understanding the pace at which the universe transformed from a simple sea of hydrogen and helium into the chemically rich landscape we see today. Each ancient star encodes information about the timing of enrichment, the intensity of star formation, and the birth of galaxies. By piecing together these clues, astronomers reconstruct a timeline that bridges the gap between the Big Bang and the complex universe of galaxies, clusters, and planets. One of the great revelations from studying relic stars is that chemical enrichment happened quickly. The first population 3 stars lived only a few million years, yet their explosions seeded their surroundings with enough heavy elements to form the next generation. By the time Methuselah and its peers appeared, only a few 100 million years after the Big Bang, the raw gas of the universe was already marked by carbon, oxygen, and iron. This rapid enrichment explains why we find no stars of pure primordial composition today. The first giants burned, exploded, and disappeared before any long-lived survivors could remain, leaving behind only their chemical echoes. The relics also reveal diversity. Not all early stars formed in the same way, nor were all enriched by the same kinds of supernovae. Some metal-poor stars show strong carbon enhancements, suggesting they formed from gas seeded by unusual explosions. Others show peculiar deficiencies in magnesium or calcium, pointing to different nucleosynthetic histories. By cataloging these variations, astronomers build a library of early star formation scenarios. It is like collecting shards of pottery from an ancient site, each fragment revealing a different aspect of a vanished culture. As observational power grows, the search for relics reaches farther. Surveys of the galactic halo continue to identify candidates with ever lower metallicities. Large telescopes on the ground, such as the Very Large Telescope in Chile, and space-based observatories like Gaia, provide the precision needed to analyze their motions and chemistry. The James Webb Space Telescope extends the search beyond the Milky Way, probing ancient galaxies at high redshift where the first stars once blazed. Though direct detection of population 3 stars remains elusive, their influence is visible in the chemical fingerprints of galaxies billions of light-years away. The survival of stars like Methuselah is a reminder of how fragile, yet enduring, the cosmos can be. Born in a time when galaxies were only beginning to form, it has persisted through billions of years of cosmic evolution, through mergers, collisions, and the birth of countless younger stars. It has carried its ancient chemistry unaltered, preserving a message from the dawn of starlight. To look at such a star today is to witness not only its present glow, but also the shadow of the universe's youth. These relics anchor our understanding of time. They show that the universe's history is not abstract, not confined to equations and models, but written in the very light of the stars. The paradox of Methuselah, once thought older than the universe, now fits within the broader pattern of consistency. The oldest stars are nearly as old as the cosmos, but not beyond it, a harmony that testifies to the accuracy of both cosmology and stellar physics. It is a fragile harmony, maintained only through constant refinement of measurements, but it is a harmony nonetheless. In the end, relics of the first generations are more than curiosities. They are living witnesses, still burning, still shining, carrying across billions of years the story of how the universe grew from simplicity into complexity. Their presence assures us that the timeline of the cosmos is not merely theoretical, but observable. By reading their light, we confirm that the universe truly is as old as we believe, and that our models, for all their uncertainties, capture a real history. The study of these relics leads us back to the central theme, the age of the cosmos, and the reliability of our measurements. If ancient stars press against the universe's boundary, then the accuracy of that boundary must be tested again and again. The next step in our journey takes us from these stellar fossils to the larger framework of cosmic history, to the shifting estimates of the universe's age through the 20th century, and the ways in which dark energy reshaped our view of time itself. The age of the universe has not always been known with the confidence we have today. It is easy to forget how recently the idea of a finite cosmic age entered science at all. For much of human history, the universe was assumed eternal, stretching backward in time without beginning. The stars in the sky were thought to shine forever, unchanging. Only in the 20th century did the cosmos acquire a birthday, a finite age that could be measured, debated, and revised. The path to the modern figure of 13.8 billion years was not smooth. It was marked by false starts, dramatic contradictions, and the gradual refinement of theory and measurement. To see how the Methuselah paradox fits into this story, we must first understand how our picture of cosmic time itself has changed. In the early 20th century, the expansion of the universe was not yet discovered. The Milky Way was thought to encompass all of space, and the idea of galaxies beyond it was still controversial. Time itself was understood in Newtonian terms, infinite and absolute. When Albert Einstein introduced general relativity in 1915, his equations suggested that the universe could not be static. Gravity would cause it to collapse, unless something opposed it. Uncomfortable with that implication, Einstein added a cosmological constant, a repulsive force that balanced gravity and kept the universe fixed. The notion of an evolving cosmos seemed implausible. This changed in the 1920s, when Edwin Hubble observed that distant galaxies are receding. Their light shifted toward the red end of the spectrum. The universe was expanding, and with expansion came the possibility of a beginning. Run the film backward, and all galaxies converge to a single point, a moment of origin. The Belgian priest and physicist Georges Lemaitre was among the first to argue for this view, proposing the idea of a primeval atom that exploded to form the cosmos. At first, the idea was met with skepticism, even derision. Some dismissed it as theology disguised as science. Yet the evidence grew, and by mid-century, the Big Bang was gaining acceptance. Estimating the age of the universe from this expansion was, however, fraught with difficulty. Hubble's early values for the rate of expansion were far too high, implying a universe only 2 billion years old. This was younger than the Earth itself, a contradiction even more severe than the Methuselah paradox. Geologists had already shown that Earth's rocks were more than 3 billion years old, thanks to radiometric dating. A cosmos younger than its planets was clearly absurd. The discrepancy exposed the fragility of measurement. It took decades of improved instruments and refined calibration to bring Hubble's constant down to realistic values, lengthening the age of the universe to a figure consistent with geology. The mid-20th century saw another debate: steady-state theory versus the Big Bang. The steady-state model proposed that as the universe expands, new matter is continuously created, keeping the density constant and the cosmos eternal. This model had no beginning, and therefore no problem of age. For a time, it was considered a serious alternative, but the discovery of the cosmic microwave background in 1965 ended the debate. The faint radiation detected by Arno Penzias and Robert Wilson was a clear remnant of a hot, dense, early universe. The cosmos had a beginning, and with it, a finite age. Even after the Big Bang was accepted, the exact age remained uncertain. In the 1990s, values for the Hubble constant still ranged widely, producing ages as low as 9 billion years and as high as 20 billion. The paradox with the oldest stars loomed large. Globular clusters were consistently dated at 12 to 15 billion years, older than some cosmological estimates. The situation was reminiscent of Methuselah, stars that seemed to outlive the universe. Once again, the resolution came not from abandoning the models but from refining the measurements. The Hubble Space Telescope played a key role, using Cepheid variables to calibrate distances with new precision. The result brought the expansion rate into line with stellar ages, easing the tension. The decisive breakthrough came in the early 21st century, with satellites like WMAP and Planck. By mapping the cosmic microwave background in detail, they pinned down the age of the universe to 13.77 billion years, with uncertainties of only a few tens of millions of years. For the first time, the cosmos had an age measured with the precision of a clock. This figure fit comfortably with the ages of the oldest stars and clusters, resolving decades of tension. The Methuselah paradox, when it appeared shortly after, was therefore especially striking. In a cosmos where everything seemed to line up, one star appeared to slip beyond the boundary. The history of cosmic age estimates shows how fragile certainty can be. A century ago, the universe was thought eternal. 90 years ago, it was 2 billion years old. 50 years ago, it ranged anywhere between 9 and 20 billion. Only in the last 2 decades has the figure stabilized around 13.8. The Methuselah paradox must be seen in this context, not as a fatal contradiction, but as another step in the ongoing refinement of cosmic time. Each paradox, from Earth's rocks to globular clusters to a single star, has been resolved by better measurements, and each resolution has strengthened the case for the Big Bang. The refinement of the universe's age was not achieved by a single breakthrough, but by the convergence of many independent lines of evidence. Each line was fragile on its own, vulnerable to errors and assumptions, but together they formed a coherent story. This is one of the great strengths of modern cosmology, its reliance on multiple approaches that test and reinforce one another. Primordial nucleosynthesis was one of the first independent checks. In the first few minutes after the Big Bang, conditions were so hot and dense that nuclear reactions forged light elements. Hydrogen was transformed into helium, along with trace amounts of deuterium and lithium. The predicted abundances of these elements depend on the density of baryonic matter, which in turn influences the expansion history of the universe. By comparing observed abundances in ancient gas clouds with theoretical predictions, scientists placed constraints on cosmic parameters that aligned with those derived from the Hubble constant. This agreement strengthened the case for a universe about 13 to 14 billion years old. Another line of evidence came from the ages of globular clusters. These dense assemblies of stars orbit the Milky Way in its halo, and their stars are among the oldest known. By fitting isochrones to their Hertzsprung-Russell diagrams, astronomers estimated their ages to be around 12 to 13 billion years. For decades, these clusters appeared older than some cosmological estimates, fueling tension. But as distance measurements improved and stellar models were refined, the cluster ages settled into harmony with the cosmic microwave background results. The clusters no longer contradicted cosmology, but confirmed it. Supernovae added yet another perspective. In the 1990s, 2 teams discovered that distant type Ia supernovae were dimmer than expected, a discovery that implied the expansion of the universe is accelerating. This acceleration was attributed to dark energy, a mysterious component that now makes up about 70% of the cosmos. The inclusion of dark energy in cosmological models reshaped our understanding of time. Without it, the universe would have slowed down more in the past, making it younger. With it, the expansion is more complex, and the inferred age fits comfortably with stellar and cluster data. The paradox of Hubble's early value was not solved merely by better numbers, but by the realization that the universe contains a force that changes its expansion over time. This historical arc shows how scientific confidence is built. Each apparent contradiction is not a failure, but a signal that something is missing. When Earth seemed older than the universe, it was a signal that Hubble's value was wrong. When globular clusters seemed older than cosmological models, it was a signal that stellar physics and distance scales needed refinement. When the Methuselah star seemed older than the cosmos, it was a signal that parallax, composition, and nuclear rates needed correction. And when the cosmic microwave background and Cepheid supernova methods yield different Hubble constants today, it may be a signal that new physics is waiting to be discovered. The story also underscores how young cosmology is as a science. Less than a century ago, the very idea of an expanding universe was revolutionary. In that short time, we have gone from infinite time to 2 billion years, to a range of ages that strained against geology and stellar physics, to a figure precise to a fraction of a percent. The Methuselah paradox is a reminder that precision is hard-won and always provisional. The age of the universe is not a number written in stone, but a value constantly tested by observation. Its apparent stability in recent decades is an achievement, but one that must be maintained through constant scrutiny. The theme that emerges is not one of certainty, but of resilience. Science does not collapse when faced with paradox. It adapts, refines, and expands. The age of the universe has been under review for more than a century, and each review has deepened our understanding. The Methuselah star is part of that tradition, an outlier that forced us to look closer, to measure more carefully, and to appreciate the delicate interplay between stars and cosmology. As we move deeper into the story, the focus shifts toward the open frontier. The Hubble tension suggests that the age of the universe may once again be revised, perhaps subtly, perhaps profoundly. The Methuselah paradox has shown us how to navigate such revisions, not with despair, but with curiosity. For in the space between measurements and models lies the potential for discovery. The shifting estimates of the universe's age reveal a pattern that is as much philosophical as it is scientific. At each stage, the cosmos seemed to challenge human expectations. The infinite universe of Aristotle and Newton gave way to the finite cosmos of Einstein and Hubble. The 2-billion-year-old universe of the 1920s collapsed under the weight of Earth's geology. The 9-billion-year-old cosmos of the 1990s was contradicted by the oldest clusters. Each paradox forced a reconsideration, and each reconsideration brought us closer to the present consensus. The lesson is that certainty is an illusion, but progress is real. The introduction of dark energy was a turning point. It reshaped not only the inferred age of the universe, but also our understanding of its future. A universe without dark energy might have slowed and eventually collapsed, its age constrained by a simple balance between gravity and expansion. With dark energy, the cosmos accelerates, stretching faster with time. This acceleration gives the universe more room to fit the ages of the oldest stars. It also raises profound questions about the fate of everything. If acceleration continues, galaxies beyond our local group will eventually slip beyond our horizon, leaving only the nearest stars visible. In that distant future, the memory of a young and vibrant cosmos will vanish. The present moment, when we can see both the relic radiation of the Big Bang and the farthest galaxies racing away, is unique. The consistency of the modern number, 13.8 billion years, is one of the triumphs of science. It emerges from cosmic microwave background measurements, from primordial nucleosynthesis, from globular cluster dating, and from the observed expansion of galaxies. It is not a number plucked from a single method, but one reinforced by many. This consistency is precisely what makes the Methuselah paradox so instructive. A single star, by seeming to step outside the pattern, forced every assumption to be tested again. When the dust settled, the paradox resolved, not by undermining cosmology, but by affirming it, demonstrating that the web of evidence is resilient enough to accommodate anomalies. The story of cosmic age under review is also a story of humility. Human beings crave definitive answers, yet the universe resists them. Each time we think we have pinned down its timeline, a new puzzle emerges. The paradox of Methuselah, the tension of the Hubble constant, the uncertainties in dark energy, all remind us that science is not about final answers, but about the pursuit of better questions. To ask how old the universe is to ask how far our methods can reach and how much our models can explain. The number itself will always carry an uncertainty, a margin that marks the boundary between knowledge and mystery. It is at that boundary that science thrives. The age of the universe is not simply a measure of time, it is a measure of our ability to read nature. From ancient myths of eternal heavens to modern equations of cosmic expansion, the journey has been one of refinement. The Methuselah star belongs to this story as both a paradox and a resolution, a challenge that sharpened our tools and deepened our understanding. In reviewing the age of the cosmos, we do not find despair in contradiction, but excitement in discovery. The next step is to explore how such paradoxes illuminate the process of science itself. Stars that seem too old, constants that refuse to agree, forces like dark energy that defy intuition. These are not flaws, but guides. They show us where to look, what to measure, and how to think differently. From cosmic age under review, we move to the broader reflection on how anomalies drive science forward, transforming puzzles into pathways. The Methuselah star became famous not because of its brightness, nor because of its beauty, but because it appeared to break the rules. To say that a star could be older than the universe is to invite contradiction, even ridicule, and yet the paradox did not collapse under scrutiny. Instead, it became a lesson in how science advances. By testing the limits of measurement, by refining assumptions, and by confronting contradictions directly, astronomy turned what looked like a failure into a source of progress. The Methuselah star should not have been, yet by existing as it did, it changed the way we think about stars, galaxies, and the cosmos itself. One of the clearest lessons is the role of anomalies in science. It is tempting to think of anomalies as nuisances, mistakes to be swept aside. But history shows that anomalies often carry the seeds of discovery. Pulsars, for example, were once mysterious signals that seemed so regular they were jokingly attributed to extraterrestrial intelligence. Quasars were once thought impossible, their luminosities far beyond what any galaxy could produce. In both cases, the anomaly forced new theories, leading to the recognition of neutron stars and supermassive black holes. The Methuselah star belongs to this tradition. Its apparent defiance of cosmic chronology was never truly believed, but it demanded explanation, and in seeking that explanation, science advanced. Another lesson is the importance of humility. Numbers can deceive when taken at face value. A central value of 14.5 billion years carried with it uncertainties of hundreds of millions of years, yet headlines declared that the star was older than the universe. The truth was subtler, but the dramatic phrasing caught attention. This tension between precision and communication is a challenge scientists face constantly. The Methuselah paradox reminds us that error bars are as important as numbers, and that the story of science is written not in absolutes, but in ranges, probabilities, and uncertainties. The paradox also revealed the power of technology. Without Gaia's precise measurements, the contradiction might have lingered, debated endlessly, without resolution. With Gaia, the distance was nailed down, and the star's age shifted into harmony with cosmology. The story shows that progress is not always a matter of new theories, but often of better instruments. Telescopes, satellites, detectors, and software, these are the engines of discovery, as essential to science as equations and models. Methuselah's paradox was solved not by speculation, but by engineering. Perhaps most profoundly, the Methuselah star teaches us about the nature of scientific knowledge itself. Science does not deal in certainties. It builds models that are provisional, awaiting revision. When contradictions appear, they are not signs of collapse, but invitations to refine. The paradox of a star older than the universe is a vivid reminder that knowledge is always incomplete, always open to challenge. Far from undermining confidence in science, this openness is its greatest strength. It ensures that progress never stops, that every anomaly becomes an opportunity for growth. The Methuselah star is not alone in carrying this lesson. It joins a long line of puzzles that have reshaped science. The precession of Mercury's orbit defied Newtonian mechanics until Einstein's relativity explained it. The ultraviolet catastrophe of blackbody radiation defied classical physics until quantum mechanics emerged. The acceleration of the universe defied expectations until dark energy was introduced. Each contradiction was a signal, and each signal led to deeper understanding. Methuselah belongs to this lineage of anomalies, not because it truly overturned cosmology, but because it sharpened our tools and clarified our models. To call it the star that should not be is not to say that it was ever truly impossible, but to acknowledge the way it stretched our confidence. It forced cosmologists and stellar physicists to confront the fragility of their assumptions. It forced instruments to be tested against their limits. It forced the community to ask whether the numbers they trusted were as solid as they seemed. In the end, the Methuselah star did not break the rules of the universe, but it bent the rules of certainty, and in bending them, it revealed their flexibility. The greatest lesson of all may be that science thrives on paradox. It is not in the places where data and theory agree perfectly that discovery happens. It is in the cracks, the mismatches, the stars that should not be, the constants that refuse to agree. Methuselah is one such crack, and through it we glimpse the resilience of science itself. The Methuselah paradox also highlights the relationship between science and public imagination. When the story broke that a star appeared older than the universe, it captured headlines around the world. For many, it sounded like a cosmic riddle with profound implications. Had science been wrong all along? Was the Big Bang mistaken? The reality was more technical, a matter of uncertainties and measurements. Yet the public fascination was not misplaced. It revealed a hunger for mystery, for the sense that the universe still holds puzzles that challenge even our best theories. Methuselah's fame shows that anomalies not only advance science but also connect it to society, reminding people that discovery is ongoing, unfinished, and accessible to wonder. This interplay between anomaly and attention has a long history. When Jocelyn Bell first detected the signals of pulsars, the regularity of their pulses was so striking that the discovery was nicknamed Little Green Men. When quasars were first identified, their spectra seemed impossible to reconcile with known physics, and they became the subject of both speculation and skepticism. Each case drew public interest precisely because the discoveries strained belief. Methuselah fits the same pattern. A star older than the universe is a phrase too provocative to ignore, even if the truth is subtler. And in drawing attention, it ensures that resources, focus, and effort are devoted to resolving the puzzle. In this way, anomalies play not only a scientific role, but also a cultural one. The star also teaches us about persistence. It took decades of work to resolve its paradox. Early parallax measurements suggested extreme ages, and for years, the uncertainty lingered. Only with the advent of Gaia did clarity arrive. This is a reminder that science often works on long timescales, with questions spanning generations of researchers. The Methuselah paradox was not resolved in a single paper or a single observation, but through the steady accumulation of data, refinement of models, and improvement of instruments. Its resolution is a triumph of patience as much as of precision. Another lesson is the interconnectedness of scientific fields. To understand Methuselah, astronomers needed stellar models built from nuclear physics, opacities from atomic physics, parallax from space engineering, and cosmology from general relativity. The paradox forced these fields to converge, to test one another, and to reconcile their results. It showed that no part of science stands alone, and that contradictions at the boundaries often become opportunities for unity. Methuselah was not just a puzzle for astronomers, but for physicists, engineers, and cosmologists alike. Its story is a microcosm of how modern science operates: collaborative, interdisciplinary, and global. Perhaps the most profound lesson is about perspective. A star that seemed older than the universe invites us to question what it means for something to have an age at all. The age of the universe is not a direct observation, but a model-dependent inference. The age of a star is not a direct clock, but a theoretical reconstruction. Both numbers carry assumptions, and both are provisional. The paradox arises when we forget this and treat the numbers as absolutes. Methuselah reminds us that science is not about certainties but about approximations, and that the approximations can always be sharpened. The paradox dissolves when we remember that the universe is not obliged to match our models exactly, but that our models are obliged to adapt to the universe. In this sense, Methuselah is a teacher of humility. It shows us that even when our numbers appear precise, they may still hide uncertainties. It reminds us that every measurement is filtered through instruments, methods, and models that can be improved. And it demonstrates that anomalies are not failures but gifts, pointing us toward the places where improvement is needed. To learn from a star that should not be is to embrace the paradox as part of the process, to see contradiction not as a threat, but as a guide. The Methuselah paradox may be resolved, but the lessons remain. They tell us that science grows, not by avoiding anomalies, but by pursuing them, not by dismissing contradictions, but by welcoming them, and not by clinging to certainty, but by accepting uncertainty as the engine of discovery. The star that should not be turns out to be exactly what science needs: a challenge, a puzzle, a reminder that the cosmos is richer than our equations, and that discovery waits in the space between data and theory. The Methuselah star endures in our imagination because it embodies the spirit of inquiry. It began as a modest point of light, faint and unremarkable, until careful measurement transformed it into a paradox. That paradox, in turn, transformed into a lesson about science itself. The star teaches us that knowledge is not a straight path towards certainty, but a winding journey through doubt, contradiction, and refinement. To call it the star that should not be is to recognize that its greatest value lies not in its numbers, but in the way it challenged those numbers. One lesson is that contradictions often exist only on the surface. The central value of Methuselah's age once appeared older than the cosmos, but the uncertainties overlapped. The apparent impossibility dissolved when the margins were respected. Science often advances by making these margins visible, by insisting that no number is complete without its uncertainty. This lesson reaches beyond astronomy. In medicine, climate science, and particle physics alike, error bars define the frontier of what we know. Methuselah stands as a symbol of this principle, reminding us that truth lies not in a single figure, but in the range that surrounds it. Another lesson is that discovery thrives on patience. Methuselah's story spanned decades of measurement and debate. For years, the star was a puzzle without a solution, an object that resisted explanation. Yet the scientific community did not abandon it. They returned again and again with better tools, refining distance, composition, and nuclear rates. This persistence mirrors the way science works across all fields, slowly, collectively, and with an acceptance that some puzzles may take generations to resolve. The star's resolution was not sudden but gradual, a slow convergence of evidence that eventually dissolved the paradox. The Methuselah paradox also illuminates the role of context. A star's age means little without the broader framework of cosmology. Only by comparing it to the age of the universe does it become paradoxical. This teaches us that anomalies are relational, emerging from the dialogue between different methods and models. It was not Methuselah alone that carried the puzzle, but the relationship between stellar physics and cosmic expansion. The paradox forced these fields into conversation, reminding us that the greatest discoveries often occur at the intersections. In the end, the Methuselah star is not an exception, but a guidepost. It did not overturn the Big Bang, nor did it stand outside the cosmos. Instead, it highlighted the limits of our methods, sharpened our measurements, and confirmed the resilience of cosmology. The star that should not be turned out to be exactly what it should be, a catalyst for deeper understanding. Its paradox is resolved, but its lesson endures that anomalies are not to be feared but embraced, for they carry the seeds of progress. As we step away from Methuselah's story, we carry with us these lessons. Anomalies ignite curiosity, contradictions sharpen precision, uncertainties invite humility. Together, they shape the scientific method, turning what seems impossible into pathways toward truth. The Methuselah star, once thought older than the universe, now shines as a symbol of this process. It is a reminder that science thrives not in certainty, but in challenge, and that the most valuable stars are often those that seem, at first glance, not to belong. From here, the narrative broadens once again. Beyond Methuselah and its lessons lies the larger question of cosmic time itself. What does it mean to assign an age to the universe? How do we distinguish between the look-back time of light and the cosmic age since the Big Bang? These are not just technical questions, but philosophical ones, for they touch on the meaning of time in a universe that is still expanding. To move forward, we must step from the lessons of one star into the broader reflections on cosmic time. When we say that the universe is 13.8 billion years old, what do we really mean? At first, the statement sounds simple, like telling the age of a person or a tree. But cosmic time is not a human clock. It does not tick in familiar rhythms, nor does it unfold in ways that are easy to imagine. The age of the universe is not a direct observation, but an inference built from models of expansion, radiation, and gravity. To understand its meaning, we must examine what kind of time we are measuring and what limits we face in doing so. The phrase age of the universe refers to the time that has passed since the Big Bang, the moment when the cosmos emerged from a hot, dense state into the expanding universe we see today. In this sense, it is cosmic time, the time measured by the expansion itself. Imagine rewinding the universe, galaxies rushing closer together until they converge. The time elapsed in that reversal is the universe's age, but this is not the same as the time we measure in everyday life. Human time is tied to Earth's rotation and orbit, to the rhythm of days and years. Cosmic time is tied to the stretching of space, to the dynamics of the universe as a whole. One way to see the difference is through the concept of look-back time. When we observe a distant galaxy, we are seeing it as it was billions of years ago, because light takes time to travel. A galaxy 10 billion light-years away is observed as it was 10 billion years in the past. Look-back time is not the same as the age of the universe, though it is related. The galaxy may have formed long after the Big Bang, so its light shows only part of cosmic history. To say that the universe is 13.8 billion years old is to place all such look-back times within a larger framework, a grand clock that began at the origin of space and time itself. This distinction becomes clearer when we think about the cosmic microwave background. The radiation we detect today was released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. When we look at that radiation, we are looking back nearly the entire age of the universe, yet not quite to the beginning. There is a horizon we cannot cross, a wall beyond which light cannot reach us. The first fraction of a second after the Big Bang remains hidden, accessible only through theoretical models of inflation and high-energy physics. In this way, the age of the universe is a boundary as much as a number, marking how far back we can reach with observation. The precision of the age, 13.77 billion years, plus or minus a few tens of millions, comes from fitting models to data. The expansion rate measured by the Hubble constant, the fluctuations of the cosmic microwave background, and the abundances of primordial elements all converge to produce the figure. Yet the number is not absolute. It depends on assumptions about the contents of the universe: dark matter, dark energy, radiation, and baryons. If those assumptions change, the inferred age changes with them. Cosmic time is therefore conditional, a measure not only of reality, but of our interpretation of reality through the lens of theory. Philosophically, this raises questions about what it means to say the universe has an age at all. If time began with the Big Bang, then the phrase "before the Big Bang" has no meaning. Asking what came before is like asking what lies north of the North Pole. Yet human intuition resists this. We are used to thinking of time as infinite, as a river that stretches both forward and backward. The idea of a beginning, a moment when time itself was born, challenges our imagination. The age of the universe, then, is not simply a number. It is a concept that redefines what time is. The Methuselah paradox gains new depth in this context. A star that seemed older than the universe was paradoxical, not only because of the numbers, but because of what those numbers represent. To say a star is 14 billion years old is to compare one kind of clock, the nuclear burning of hydrogen, with another, the expansion of space. The paradox reminds us that these are not the same clocks. That they agree as well as they do is remarkable. That they occasionally appear to disagree is inevitable. The challenge is not to eliminate disagreement, but to understand what it teaches us about the nature of time itself. The meaning of cosmic time is therefore layered. It is observational, tied to the light we see from distant galaxies. It is theoretical, tied to models of expansion and matter. And it is philosophical, tied to the question of whether time had a beginning or whether it is an emergent property of the universe. To grasp the age of the cosmos is to stand at the intersection of science and philosophy, measurement and imagination. To understand the age of the universe, it is helpful to imagine different clocks ticking across cosmic history. One clock is nuclear, set by the fusion of hydrogen into helium inside stars. Another is dynamical, set by the expansion of space itself. Still, another is radioactive, set by the decay of uranium or thorium. Each of these clocks runs on a different mechanism, yet all of them point to a consistent picture. The fact that stellar ages, radioactive decay timescales, and cosmic expansion all converge near 13 to 14 billion years, is extraordinary. It shows that nature, despite its complexity, can be read in harmony through different measures of time. And yet harmony does not mean perfection. Each clock carries its own uncertainties, and those uncertainties are never zero. Stellar models depend on assumptions about opacities, convection, and nuclear rates. Radioactive decay ages depend on the difficulty of measuring faint spectral lines. Cosmic expansion ages depend on the value of the Hubble constant and the composition of dark energy. Each method has error bars, and those bars sometimes overlap, only barely. When the Methuselah star appeared older than the cosmos, it was a reminder that uncertainties can stack in ways that produce apparent contradictions. The paradox dissolves once the full range is considered, but it teaches us not to treat any clock as infallible. The concept of cosmic time also highlights the relativity of measurement. In Einstein's theory, time is not absolute, but woven with space into a single fabric. The passage of time depends on the observer's motion and gravitational environment. For cosmic time to be defined at all, we must imagine a special kind of observer, one who moves with the expansion of the universe and sees it as homogeneous on large scales. This is not any real observer, but a construct, a cosmic average. The age of the universe is therefore the age as measured by this ideal observer, not by any individual galaxy or star. This abstraction does not diminish the concept, but it reminds us that cosmic time is not the same as human time. Another subtlety is that cosmic time does not extend indefinitely backward. According to general relativity, the equations describe a singularity at the Big Bang, a point of infinite density and zero volume. But many physicists believe this singularity is a sign of incomplete theory. Quantum gravity, still undeveloped, may smooth out the beginning into something less absolute. Some theories of inflation suggest that the universe underwent a rapid expansion from a quantum field state, with no true singularity. Others propose cyclic models, in which expansion and contraction alternate. If such ideas are correct, then the phrase, age of the universe, may itself be provisional, applying only to the current phase rather than to all of existence. This uncertainty does not diminish the achievement of modern cosmology. To measure the age of the universe to within tens of millions of years is remarkable, but it places the number in perspective. The universe is 13.8 billion years old, give or take, according to our best models, but the true story of time may be richer, extending beyond what our current theories can describe. The Methuselah paradox is a reminder of this richness, showing that even small discrepancies can point to deeper truths. The meaning of cosmic time is also shaped by philosophy. For centuries, thinkers debated whether time is an independent backdrop or a measure of change. Isaac Newton saw time as absolute, flowing uniformly regardless of the events within it. Gottfried Wilhelm Leibniz argued that time has no existence apart from change itself. Modern physics leans toward the latter view. Cosmic time is not a stage on which the universe plays, but part of the play itself, inseparable from matter, energy, and expansion. When we say the universe has an age, we are describing not something external but something emergent, a property of the cosmos in motion. The Methuselah star, by pressing against the boundary of cosmic time, forces us to confront these questions. What does it mean for a star to be nearly as old as the universe? What does it mean to compare the nuclear burning of a single object with the expansion of all space? The answer lies in recognizing that time is not one thing but many, and that our task is to translate between them. Cosmic time and stellar time are different languages, and the paradox arises when we forget that translation is never perfect. Cosmic time invites reflection not only on physics, but also on human perspective. For us, billions of years are almost inconceivable. A century is long in human affairs, and a millennium is the span of civilizations. To speak of 13.8 billion years is to step far outside the scale of our experience. And yet, it is within this scale that the universe's story unfolds. The oldest stars, the faint glow of the cosmic microwave background, the galaxies at the edge of observation, all remind us that human life occupies only the briefest sliver of cosmic time. To measure the age of the universe is to situate ourselves in a vast chronology, humbling in its immensity and inspiring in its coherence. This coherence is fragile, held together by theory, observation, and the constant refinement of both. The Methuselah paradox is a case study in how easily harmony can be disturbed. A single star appeared to exceed the universe's age, and for a time, the consistency of the entire framework was questioned. That the paradox was resolved is a testament to the resilience of science, but it also underscores how delicate the balance is, how much depends on precise measurement, and how provisional even our most confident numbers must remain. The meaning of cosmic time, then, is not in the illusion of certainty, but in the ongoing process of refining our understanding. The distinction between look-back time and cosmic age deepens this reflection. Every image of a distant galaxy is a window into the past, a fragment of history carried by light across billions of years. The farthest galaxies we observe are seen as they were only a few 100 million years after the Big Bang. The cosmic microwave background shows us the universe when it was less than 500,000 years old. These look-back times are profound, but they are not the same as the age of the universe. They are glimpses of chapters within a book, while cosmic time is the length of the book itself. To confuse the two is to miss the difference between pages and the story as a whole. Philosophically, the question of cosmic time touches on the boundaries of what science can know. The moment of the Big Bang is hidden from observation. We cannot see through the first fraction of a second, and our theories there are uncertain. Inflation, quantum fields, and multiverse hypotheses offer possibilities, but none is confirmed. The universe may be older in some deeper sense, or it may truly have begun at the Big Bang. The age we assign is therefore not only a measurement, but also a declaration of the limits of knowledge. It is an answer that acknowledges its own incompleteness. The Methuselah star shows us how this incompleteness works in practice. For a time, the star seemed to reveal a contradiction, an object outside the cosmic boundary. But the contradiction was not fatal. It was an invitation to refine our instruments, our models, and our assumptions. Once refined, the star's age fit within the boundary, after all. The lesson is that cosmic time is not absolute but flexible, shaped by what we can measure and how well we can measure it. Its meaning lies not in a static number, but in the dynamic process of inquiry. In the end, to ask about the meaning of cosmic time is to ask about our place in the universe. We are creatures bound by short lifespans, living on a planet a few billion years old, orbiting a star halfway through its own life. Yet we have learned to measure the age of the cosmos itself, to place our moment within the grand arc of 13.8 billion years. The paradox of Methuselah and the precision of modern cosmology alike remind us that time is both the most familiar and the most mysterious of dimensions. We live within it, yet we struggle to define it. The meaning of cosmic time lies in this tension, in the recognition that we can measure the universe's age even as we marvel at its depth. From here, the story moves toward resolution. The Methuselah paradox is no longer a threat to cosmology, but a reminder of how science grows. In the next step, we draw the threads together, seeing how a star that once seemed older than the universe has become part of a larger narrative of refinement, resilience, and discovery. The Methuselah star no longer stands as an impossible object. With Gaia's precise distance measurements and refinements in stellar physics, its age has settled at about 13.5 billion years, with an uncertainty of several 100 million years. That number places it comfortably within the cosmic boundary of 13.8 billion years. The star is ancient, but not older than the universe. The paradox that once seemed to threaten cosmology has been resolved, at least for now. This resolution is not trivial. It reflects decades of work, thousands of observations, and the collaboration of scientists across disciplines. To reach it, astronomers had to measure the star's distance with unprecedented accuracy, model its interior with refined nuclear reaction rates, and compare its properties to those of countless other ancient stars. Each step reduced uncertainty. Each refinement narrowed the gap until the paradox dissolved into consistency. The story is a triumph not only of measurement, but of method, showing how science confronts contradictions and emerges stronger. Yet the resolution is also provisional. The age of the universe is still under debate, shaped by the tension between different measurements of the Hubble constant. If the higher value of 73 kilometers per second per megaparsec proves correct, the universe may be closer to 12.5 billion years old. In that case, Methuselah would once again press uncomfortably against the cosmic boundary, though perhaps without crossing it. The paradox would return, not as an outright contradiction, but as a renewed challenge. The lesson is clear. In science, resolutions are always temporary, awaiting the next round of data. The phrase, "for now," captures the essence of this story. The Methuselah paradox is resolved for now, just as earlier contradictions were resolved in their time. Earth once seemed older than the universe, until the Hubble constant was corrected. Globular clusters once seemed older than cosmology, until stellar models improved. Methuselah once seemed older than the cosmos, until Gaia refined its distance. Each paradox was temporary, and each resolution deepened our understanding. But the possibility of new paradoxes remains, and it is in those paradoxes that science finds its vitality. The resolution of Methuselah's paradox also reveals something profound about knowledge itself. Certainty is rare, and when it appears, it is fragile. Numbers like 13.8 billion years carry an aura of precision, but they are built on layers of assumptions, models, and instruments. To treat them as absolute is to forget the provisional nature of science. Methuselah reminds us that even precise numbers can shift, that even stable models can bend, and that knowledge is always a work in progress. Far from being a weakness, this provisionality is the strength of science, for it ensures that our understanding remains open to revision. For the public, the story may seem anticlimactic. A star once thought older than the universe turns out not to be. But for scientists, the resolution is thrilling. It means that the tools work, that the models are robust, and that anomalies can be explained without abandoning the framework. The Big Bang remains intact, not because it is immune to contradiction, but because it has survived every test. Methuselah's paradox, like others before it, has strengthened the case for the Big Bang by forcing it to prove itself against scrutiny. The phrase "resolved" for now also points to the future. New telescopes, new surveys, and new missions will continue to push the boundaries of precision. The James Webb Space Telescope will probe ancient galaxies, revealing conditions close to the first billion years. The Nancy Grace Roman Space Telescope will map supernovae across cosmic history. Ground-based observatories will refine the Hubble constant with gravitational waves and galaxy clustering. Each new dataset carries the possibility of renewing old paradoxes or creating new ones. The Methuselah star may be resolved, but the story of anomalies in cosmology is far from over. The resolution of the Methuselah paradox also illustrates how science depends on instruments as much as on theory. Without Gaia's exquisite parallax data, the star might still appear anomalous. Earlier distance estimates were uncertain by several percent, enough to shift the inferred age by hundreds of millions of years. A small error in distance translates into a large error in luminosity, and luminosity is the key to understanding a star's evolutionary state. Once Gaia provided its precise measurement, the uncertainty collapsed, and Methuselah's age adjusted into harmony with the cosmos. This is a reminder that our understanding of the universe is inseparable from the tools we build to study it. Each leap in technology is also a leap in knowledge. The paradox also reflects the importance of collaboration. Stellar physicists, cosmologists, nuclear physicists, and observational astronomers all contributed to the solution. Each field brought its own expertise, from modeling convection in stellar interiors to measuring isotopic abundances to refining distance scales. No single discipline could have solved the puzzle alone. The resolution was a collective achievement, showing how modern science thrives at the intersections of knowledge. Methuselah was not just a star, but a meeting point for diverse branches of inquiry, and its paradox became a stage on which collaboration played out. At the same time, the paradox highlights the fragility of consensus. For years, Methuselah's age hovered uncomfortably close to the edge of the universe's timeline. Some suggested that the tension was evidence of deeper problems, perhaps even flaws in cosmology itself. The fact that the paradox resolved with better measurements does not mean that all such tensions will resolve so cleanly. The Hubble constant debate remains unresolved, and future anomalies may prove more resistant. The lesson is that consensus is never final. It must be earned and re-earned with each new observation. The provisional nature of the resolution is not a weakness, but a strength. It shows that science does not cling to conclusions, but tests them relentlessly. If Methuselah's age had remained older than the universe, the scientific community would not have ignored it. They would have re-examined the Big Bang, tested new theories, and sought explanations in uncharted territory. The fact that the paradox dissolved instead reinforces confidence, but it also demonstrates readiness to confront deeper contradictions, should they arise. Science survives by being open to revision, not by insisting on certainty. The Methuselah star also serves as a lesson in communication. When newspapers declared that a star was older than the universe, the story captured public imagination, but also risked misunderstanding. To many, it sounded like proof that science was wrong. In truth, it was proof that science was alive, grappling with uncertainty. Communicating the nuance of error bars and uncertainties is difficult, but essential. Methuselah teaches not only scientists, but also storytellers that anomalies are not embarrassments, but opportunities to show how knowledge grows. The phrase "for now" carries humility. It acknowledges that the resolution may not last, that future discoveries could reopen the paradox, but it also conveys confidence that science is ready. The history of cosmic age shows this pattern again and again. Earth older than the universe, clusters older than cosmology, Methuselah older than the cosmos. Each paradox tested science, and each resolution strengthened it. The next paradox will do the same, and the cycle will continue. This is the rhythm of discovery. The resolution of Methuselah's paradox, therefore, belongs to a larger narrative. It is not the end of the story, but a chapter in the ongoing dialogue between observation and theory. The star no longer threatens cosmology, but it continues to inspire reflection on how anomalies drive progress. Its paradox was resolved, but the universe remains full of puzzles, waiting for the next star, the next constant, the next measurement, to challenge our confidence once again. The Methuselah star's paradox may be resolved, but its legacy endures. It showed that the smallest cracks in our models can open into profound questions, and that those questions can lead to sharper clarity. The star that once appeared older than the universe became a symbol of scientific resilience, a reminder that anomalies are not the downfall of theories but their proving ground. Its light carries not only the story of its own long life, but also the story of our struggle to measure time on the largest possible scale. The resolution also invites us to think about what it means to know. Science never grants final answers, only provisional ones. To say that the universe is 13.8 billion years old is to state the best result of our models today, not a timeless truth. To say that Methuselah is 13.5 billion years old is to accept that this estimate rests on assumptions about nuclear physics, stellar atmospheres, and cosmic composition. The truth may shift with new discoveries, but this is not a weakness. It is a strength, for it keeps science alive, questioning, and open to correction. In this way, Methuselah's story is not just about astronomy, but about the method of science itself. It reminds us that the most valuable questions are those that seem impossible, the ones that force us to push instruments to their limits and theories to their breaking points. A star that should not have been became the star that taught us how to be cautious, how to be precise, and how to embrace uncertainty. The broader lesson is that the universe is not fragile. Our models may falter, but the cosmos remains what it is, vast and enduring. When a paradox arises, it is not the universe that is at fault, but our description of it. Methuselah reminds us that reality is always the measure, and that our task is to align our understanding with it. In doing so, we find not despair in contradiction, but wonder in the process of discovery. As the narrative closes, the Methuselah paradox stands as a completed chapter, but not the final one. Other puzzles await the Hubble tension, the mystery of dark energy, the search for population 3 stars, the quest to understand what happened in the first instant after the Big Bang. Each may one day produce its own paradox, its own moment of contradiction, its own test of resilience. And when it does, Methuselah will remain a guide, showing us that paradoxes are not dead ends, but stepping stones. The star that should not be is, in truth, the star we most needed. Its paradox resolved, it continues to shine, carrying across 190 light-years the light of 13.5 billion years of history. It tells us that no star is older than the universe, but that in seeking to answer the question, we measure the limits of knowledge itself. And in those limits, we find the true meaning of science, not the certainty of answers, but the endless pursuit of understanding.